Good morning, everyone. Am I audible?
Yes, Mosumi, you are audible.
Okay, thank you. Good morning. So we are waiting for Director Sir. Good morning, everyone. Good morning, sir.
Good morning.
Okay. Yes, let's start now, sir.
Yeah. Please go ahead.
Okay. So, good morning, ladies and gentlemen, and dear colleagues and students. I am Moshumi Basu from Department of Physics, IIST Shibpur. It's a great pleasure for me, as well as my department, to welcome all the participants for this 3-day international webinar on advances in electronic, optoelectronic, photonic materials and devices. A glance through this list of presentations planned for the next 3 days reveals an amazing diversity of their real-life applications. I welcome all the eminent speakers and guests from all over the country and abroad. This is the first international event in the history of our department which is completely conducted on a digital platform with the social distancing norms due to COVID-19 pandemic. So in this program, we all will be enriched a lot from the renowned personalities in the field of photonics, electronic, and optoelectronic materials and devices. So it is to be mentioned that to match the time difference between our country and other countries like Italy, France, Taiwan, United States, we had to schedule the program in 3 sessions of morning, afternoon, and evening. I request all the participants to mute themselves during any presentation, and after the talk, if they have any question, send it by chat box. Host and chairpersons of the sessions will convey those questions to speaker. So I earnestly request all participants to maintain this decorum throughout the event. So those who are observing the online streaming of the program through YouTube, please send your question in the chat box there, and our technical representative will convey those to speaker. Now I request the chairman of the organizing committee of the webinar, Dr. Krishnendu Mukherjee, our head of the department, to deliver the welcome address.
Thank you, Moshumi, for your introduction. Our Honorable Director, Professor Parthasarathi Chakraborty, Dean Academic, Professor Sudip Roy, Dean Research and Consultancy, Professor Shubhasish Bhaumik, Dean International Relation and Alumni Affairs, Professor Arindam Vishwas, Chairman CEP Cell, Professor Sudip Kumar Chattopadhyay, distinguished speakers and guests of the webinar, my esteemed colleagues, my beloved friends, and my dear students. I welcome you all to this international webinar on advances in electronic, optoelectronic, photonic materials and devices. We know that it is an emerging field of research in the arena of science and engineering. The talented researchers from different disciplines have been contributing in this area almost since last few decades. It is quite obvious.
Please unmute. Krishnendu, Dr. Krishnendu, please unmute.
Sorry, it is not audible, right? Am I audible?
You
Yes,
are audible now. Go ahead. Go ahead.
Okay. Thank you, Moshumi, for your introduction. The Honorable Director, Professor Parthasarathi Chakraborty, Dean Academic, Professor Sudip Roy, Dean Research and Consultancy, Professor Shubhasish Bhaumik, Dean International Relation and Alumni Affairs, Professor Arindam Vishwas, Chairman CEP Cell, Professor Sudip Kumar Chattopadhyay, distinguished speakers and guests of the webinar, my esteemed colleagues, my beloved friends, and my dear students. I welcome you all to this international webinar on advances in electronic, optoelectronic, photonic materials and devices. We know that it is an emerging field of research in the arena of science and engineering. The talented researchers from different disciplines have been contributing in this area of research almost since last few decades. It is quite obvious that the future growth or future advancement of technology will depend more upon the outcome of this area of research. In general, we know that the flow of charge in solids or the propagation of light in fiber, it is basically described by one of the fundamental interactions in nature. It is due to interaction of radiation with the matter, commonly known as quantum electrodynamics. In the fundamental level, it describes the interaction of photons with electrons. Here, photons are basically the energy packets of the radiation with which the light is made of. The frequency of radiation, which are basically responsible for working of this photonic device, mainly falls in the visible region or in lower frequency region like infrared or microwave. It is needless to mention that the small device we always carry with us, our mobile phone, working of which is basically governed by the laws of quantum electrodynamics.
Dr. Krishnendu Mukherjee, please unmute. Please unmute.
So I again welcome you all for being with us here this evening. Good morning, all of you. Thank you very much.
Thank you, Dr. Mukherjee, for your welcome address. Now, I request Professor Subhashish Bhaumik, Dean of Research and Consultancy, IIST Shibpur, to say something on the occasion.
Honorable Director, IIST Shibpur, Professor Partha Chakraborty, Dean Academics, Professor Sudip Kumar Roy, Dean International Relations and Alumni Affairs, Professor Arindam Vishwas, eminent experts and invited speakers, Professor Sudip Kumar Chattopadhyay, Coordinator, CP Program, Professor Krishnendu Mukherjee, Head of the Department of Physics, faculty members, and the participants. A very warm welcome and very good morning to all of you. It is indeed a moment of pleasure to note that the Department of Physics is organizing this online webinar on advances in electronics, optoelectronics, photonics materials, and the devices. Electronics and the photonics materials like semiconductors, superconductors, ferroelectrics, liquid crystals, conducting polymers, nonlinear optical, and the optoelectronics materials, electrochromic material, laser materials. So these are the key elements of continued scientific and the technological advances in the 21st century. Electronic and photonic materials, these are expected to grow to $1 trillion industry in the new millennium and will be the most exciting dominating force in the emerging new technologies in the field of science and engineering. Most of the electronic and the photonic materials and the devices, they are less conspicuous to our senses, but together they have played an indisputable role in defining the way the people live, work, and communicate in the 21st century. So from the microprocessors containing billions of transistors, which provides the immense computational power, to the laser diodes and the radio frequency transceivers, which enables the transglobal and the wireless communications. Hope the experts will discuss the synthetics, processing, fabrication, spectroscopy, physical properties, and the exciting applications of the electronics and the photonics materials, covering everything of today's and developing the future technologies. Faculty members of the physics department, they are carrying out number of sponsored research projects in the relevant fields, and the department has rightly selected an area which creates a lot of interest and concern among the scientists and the engineers. I hope all the participants will get enough knowledge and informations to carry out further interdisciplinary research and implement the know-how in solving the industrial problems. Thank you.
Thanks a lot to Professor Bhaumik for your speech on this occasion. Now I am requesting Professor Sudip Rai, Dean Academic, to say a few words on this webinar.
Good morning, respected Director Professor Partha Chakraborty, Dean Research and Consultancy Professor Subhashish Bhaumik, Dean International Relations and Alumni Affairs Professor Arindam Vishwas, Coordinator QIP and Continuing Education Program, Professor Sudip Kumar Chattopadhyay, Head of the Department of Physics, Professor Krishnendu Mukherjee, coordinators, faculty members, and participants, and the students. It is really a great pleasure for me to be able to take part in the inaugural program of the international webinar on advances in electronic, optoelectronic, and photonic materials. It is being organized by Department of Physics. Already, Professor Bhaumik has elaborated the role of these materials in the present day life. Our present day, the digital revolution that has been made our life more easy. We can now have all the information in a simple mobile, and the distant places, whether it is in other part of the globe, it is now very close to us. So it become possible due to emerging of new materials. And in this case, these the materials, the optoelectronic and photonic materials have great role to play. In the present, the pandemic situation, when every sphere of our life is very much disturbed, even then we are able to continue our most of the activities. That is due to the development of newer materials, and which is able to give us the information from distant places. Also, we are able to get different gadgets due to the development of these new materials. The Department of Physics has a great of these of IIST Shibpur has a great role at playing in playing in this arena for long time. The faculty members of this department, they are devoted wholeheartedly in the research work. They are regularly, the scholars are, they are regularly producing PhD scholars, and their publications and other involvement in different spheres of physics is really a praiseworthy effort. In this program, in this international webinar, I expect that the participants will be highly benefited, and after this program, they will gain much in this newer field, and they will also devote themselves in newer research work and newer research fields. I understand the number of international experts will be participating, and they will be delivering lectures in this program. And I congratulate the coordinators for taking the effort of organizing such a good international webinar. Finally, I like to say my best wishes to all the participants of this program. Thank you. Thank you all.
Thank you, Professor Rai, for your nice words. Now I have a request to our Honorable Director, Sir Professor Parthasarathi Chakraborty, the Chief Patron of the organizing committee, to kindly deliver the inaugural speech for this event.
Good morning, my esteemed colleagues, the distinguished speakers, and participants in this 3 days webinar organized by the Department of Physics on a very interesting topic, advances in electronic, optoelectronic, and photonic materials and devices. As the previous speakers has already explained the importance of this, and I'll further try to throw some light on this, because this is a subject which is very close to my heart, and I wish I could deliver a lecture on this occasion, but because of my administrative compulsion, probably I'll not be able to make it. And as you know that because we are going through a pandemic situation, we had to organize this on the digital platform. However, it is always better when we interact physically, and we hope that in near future we'll be able to have this kind of program on the campus, right, where you can physically interact with people. I must congratulate at the onset the Department of Physics for organizing this event, the head of the department and his team, and particularly the coordinators of the program. Now, to be very honest, that this area is a very vast area for a conference to be organized. These days the culture is that to organize conferences on focused area, right? But this is rather a broad and vast area of talking about electronic, optoelectronic, and photonic materials. So, and devices there. Now, if we go back to history, let us see how all this development of the field of electronics has taken place. Dr. Basu, I can talk for 10-15 minutes.
Okay, okay. If it is more
You,
than, no problem.
you give me the time so that I
No,
do
no,
not
no,
exceed
no,
this.
no, 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 sir.
Because of the problem that when they start talking, they don't know where to stop.
No, no,
So,
no, no, sir. No problem.
So 10 to 15 minutes I'll take.
No problem.
So let us see the journey of electronics very briefly, particularly for the beginners who are in this field working on electronic or optoelectronic or photonics. It all started in 1904. We say that the field of electronics engineering was born in 1904 with the invention of vacuum tube, right, which you knew as bulbs, electronic bulbs, in 1904 by Fleming. He was the inventor. And the early electronic devices were based on these vacuum tubes or bulbs. Unfortunately, Fleming was not given the patent right for his invention, but that is considered today as the birth of electronics in 1904. Even though Fleming got a lot of awards, even that Institution of Radio Engineers Award, which is IEEE now, and knighthood also he got, but he didn't get the patent right for his invention. Later on, tetrode valves, triode valves, tetrode valves, pentode valves, lot of vacuum tubes were developed. And in the Second World War, these vacuum tubes played a significant role and saved the British to a large extent. But during this, for nearly 50 years, these vacuum tubes ruled the semiconductor industries existing on those days, both in civil situation as well as in military situation. And civil situation, one of the application was in hearing aids, making electronic hearing aids, where those who are short of hearing, they used to have this device where the signal is amplified and fed to ear, and this used to be very bulky because of the use of these vacuum tubes, which are very bulky, and weight was also, they were heavy also. During Second World War, and near to that, now people started working on the tiny semiconductor crystals, right? Initially it was germanium and silicon. And Bell Labs, if you see, the contribution of Bell Labs has been immense in the field of developing semiconductor devices and many optoelectronic devices also. So using this tiny semiconductor crystal, it was possible to make a diode which works very similar to your bulbs, vacuum tube, which was invented by Fleming. And then people started working on these semiconductor crystals, right? And as you know that both germanium and silicon, they belong to group 4 of the periodic table, and they are elemental semiconductor. And many people started working on this material. Now, why this topic is important? Because if you see from this Second World War period, and there's a tremendous development in the field of semiconductors uh, because of new generation materials which have come in. That has changed over the last 2 decades. There's a tremendous change because of the new materials which have come. You must have heard about graphene, carbon nanotubes, which are coming in a big way. But nevertheless, silicon is still ruling the semiconductor industry today. That you must understand. And none of these materials which have been developed in the recent year can really replace silicon, particularly in the field of microelectronics, the integrated circuit chips which you use, right? Even though we talk lot about your nano electronic devices, but this will not replace the microelectronic devices which are still ruling, which you know as different names as VLSI and other thing, whatever you talk. Semiconductor is still, the silicon is ruling the semiconductor industry. But prior to that also, if you see the history, I'll not get into details. In 1904, so J.C. Bose had a patent where a semiconductor material was used and a metal wire against it, and which could be used for detection of radio waves, radio wave detectors. And he held a patent as early as 1904. But the real work started after Second World War. And Shockley is one of the researchers who believe that it is possible to make a semiconductor version of a triode valve. The triode valve can amplify a signal. So he believed in that. So he, in Bell Lab, he started working with two of his juniors, Bardeen and Bratton, and they developed the transistor at Bell Lab. Unfortunately, when Shockley was the leader of the team, but Shockley didn't get the credit because when Bardeen and Bratton tested this first transistor, Shockley was unfortunately not present. So he didn't get that. But later on, Shockley developed a different version. The first transistor which was developed was known as point contact transistor, which was developed by Bardeen and Bratton. They patented it also later on. But Shockley was quite annoyed with Bardeen and Bratton, and he started working himself and developed junction transistor. Right? It's a different the transistor, you know, bipolar junction transistor today is junction transistor, which was invented by Shockley alone. Shockley did the demo. Later on, all the three shared the Nobel Prize in 1958. They got the Nobel Prize. So that was the first turning point in the field of electrolysis, the development of transistor. But again, if you see the history in the beginning, the transistor didn't get much attention of the people, neither the researcher nor the press. No one gave any importance initially to the transistor. Anyway, Bell Lab started publicizing this transistor, and they're expecting it will hit the market, and eventually it did. And after several years, and then Shockley had some problem with Bell Lab, and he left the Bell Lab and started his own lab, Shockley Semiconductor Lab, Northern California, and which you today know as Silicon Valley. Right? He was the first person to bring silicon to Silicon Valley. Shockley developed his lab, and some of his colleagues also joined your Shockley's lab from Bell Lab. But soon Shockley, because of his attitude, Shockley had some problem with the his fellow, and they left and they developed Fairchild, a new industry. And initially, they are in a dilemma whether to continue work with germanium or both germanium and silicon. And at one point of time, Shockley decided that he will not work any further with silicon. But your Fairchild, and there's subsequently a lot of other labs which came out. Their origin was from Fairchild. You know about Robert Noisy and your Gordon Moore and other people who were responsible for creation of Intel, then AMD. So all this actually originated from the Fairchild. And there was a tough competition amongst this semiconductor industry. So Shockley first created the lab in the Silicon Valley, and he trusted more on the university graduates rather than established researcher in the field. And they started working, and there's huge competition among all these giant companies of IC making companies, manufacturing companies like Intel, AMD, IBM, Fairchild, they are making. So another turning point in semiconductors came with the invention of integrated circuit. So IC. So Robert Kilby was one inventor, and Noisy was another inventor. They had slight differences in the concept of IC. It is built on one substrate. The entire circuit is based on. But interconnection, there was some difference. I'm not getting into this detail. So this is another turning point, the invention of integrated circuit. Then the MOS technology came, and after MOS technology, your development was in leaps and bounds in the field of electronics. And as Professor Bhumika said, it is $1 trillion in industry still today in Silicon Valley that invested for IC manufacturing. So the material which earlier used to be was silicon. The semiconductor material is silicon, right? As you know that silicon, the raw material used for silicon is basically sand, SiO2, which is used for making. So you get the CPU chip from sand basically. If you, in a very crude way, if you say that you use sand for making CPU chips, but there are a lot of processing steps to go. So these electronic devices, you know that electronics has revolutionized the entire field, how it occupied the commercial markets. There's a lot of electronic devices came. One of the biggest one, the first step was they replaced the electromechanical calculator, which used to be there, by small pocket size calculator. That was a big turning. Now, in the field of electronics engineering, if you see that there are many areas, but the primary development in all areas, so for example, in the area of communication, right? The electrical communication, which you understand. The development in the field of electrical communication or even in optical communication, everything has been possible because of the parallel development in the field of semiconductor devices. That's very important. Because any electronic system you go for, whether it's for any purpose, for instrumentation purpose, for communication purpose, anything you go, basic devices are used there in those systems, electronic systems. So unless there is a development in the field of your devices, there cannot be development in any other field of electronics, right? So this is briefly the history, but later on, then many people started, you know, there is another class of materials which are called compound semiconductors. Right, these compound semiconductors are obtained by mixing your materials, making compounds of materials from different groups. Say group 3 and group 5, you know, gallium arsenide is a material which is very interesting semiconducting material and whose properties are better than silicon in many respects. So gallium arsenide, indium phosphide, indium arsenide, aluminium arsenide, these are all 3,5 semiconductors. So these semiconductors are called compound semiconductors. Likewise, you can take one group 2 and one group 4. One group 2 and one group 6. So that you have 8 electrons in the outermost orbit, which gives you a stable structure, like that crystalline structure which you get in silicon kind of thing with 8 electrons in the outermost orbit by a central silicon atom sharing electrons with 4 adjacent silicon atoms make a structure. So you can have 2,6 compound, you can have 4,4 compound, like silicon carbide is another interesting material. Now this lot of 3,5 materials, I'll not get into the details because of shortage of time. These semiconductors, you can make further alloy semiconductors using this 3,5 material or 2,6 materials, right? Like say aluminum gallium arsenide is an example of a 3,5 ternary semiconductor, where you use 2 group 3 element and 1 group 5 element. Likewise, you can have 1 group 3 and 2 group 5 element, say indium arsenide antimonide. So arsenic and antimony are from group 5. So it's a ternary semiconductor. Likewise, you can have two group 3 elements and two group 5 elements make a quaternary semiconductor. And all the semiconductors have different band gaps. And these semiconductors have all the parameters which are different from each other. Even you have the flexibility of changing the percentage of this material content in the semiconductor, and you can virtually tailor the property of the material. That's the biggest advantage now we have. Why the material is so important. Now we are in the age where you can tailor the property of the material. We were in the age we started with germanium and silicon, and then we had the limitation that any device you develop, your material is fixed, and you cannot change the intrinsic properties of the material. Right. So they will be, if the mobility is something, then mobility will be like that. You cannot change. But now you have a flexibility of tailoring the properties of the material. Right. So that's a big advantage. I can tailor the band gap of the material. And many all these properties I can, lattice constant, everything I can change the material. So that's a big opportunity. Now today you can design a material to suit your requirement, device requirement, right? So these P5 materials give you enormous flexibility, and they can easily give you heterojunctions, right? So these heterojunctions have their applications. We talk about all optoelectronic and photonic devices. Most of the devices are your heterojunction devices. So 3-5 materials in the beginning, they were becoming very popular because their properties were superior to silicon. But the problem with 3-5 materials is that they are more expensive. Their fabrication is also very, very sophisticated system is required. So cost-wise, it becomes very high and it cannot compare with silicon. So initially, there was a lot of your 3-5 labs were open that people started working on 3-5 materials. But 3-5 materials, all the devices which are based on silicon were replicated by using these 3-5 materials. But because of their high cost, they could not compete with silicon, most of them. But there are certain devices, heterojunction devices, as you know about heterojunction field effect transistors, or your HEMT, high electron mobility transistor, heterojunction bipolar transistors. These are some of the devices where you use this 3-5 material. Otherwise, silicon is still ruling this. And this increase is that the integration capacity, we talk of VLSI or ULSI, ultra large scale integration, where we are putting trillions of transistors together in silicon. But, and I don't know, those who are in the field may be knowing about Moore's law, who predicted that every 1.5 years, the number of your devices you can put in the IC, that IC is a stamp size IC, the die increases twice. And industry follows almost the Moore's law. But now we have come to an end by squeezing the size of the device to an extent that physically it will not be possible to reduce the size of the devices anymore. So this is a big challenge. So is it the end of Moore's era where this Moore's law will be valid? Now we'll have to think of other options, right? And nanotechnology created a lot of hope among the people, and a number of nanoelectronic devices were also developed, like single electron transistor, resonant tunneling transistor, and resonant tunneling diodes. So all these devices were developed using this nanotechnology. But these devices cannot replace that silicon in your microelectronic circuits, like the central processing unit, microprocessor chips. They cannot be replaced. So it is believed that these devices can probably supplement the functionalities of your traditional microelectronic chip. But with the invention of your graphene and carbon nanotube, people started applying those concepts in semiconductor devices, because you know that silicon, because of its that CMOS technology's development, that has become one universal platform. So whenever you make some devices, we first try to find whether it is compatible to silicon platform or not, right? And people started using this graphene and carbon nanotube also for making these transistors. And these transistors actually have been tried, and they are trying to make use of carbon nanotube, CNT FETs, and IBM with Stanford University, they have developed IC, which will be based on your carbon nanotubes on the silicon platform. It's a little complicated technology, but they are thinking that probably this will be the future of CMOS, but you never know. You never know. So this is all about the development which is taking place in electronics. We are at the crossroad now, the VLSI technology, that which way to go, right? And I don't know if your quantum computation and this thing is successful, then probably it will take us in a different direction. Otherwise, I believe that silicon with this technology is going to stay for some more time with some addition with graphene and carbon nanotubes maybe there. But these new materials have posed really challenges before silicon, right? Because they had certain properties, particularly when you get in the nanostructure form, you get a lot of properties which you normally cannot get from silicon, right? So these materials are really becoming challenging. I think in this conference, you learn about this new generation materials coming. A few more points I'll just touch upon. Optoelectronics and photonics. This is another interesting thing that are they same or they are different. Photonic devices, in many books you'll find that the same devices are discussed in as photonic devices, and many books it is called optoelectronic devices. This is also very interesting for the beginners to know. Optoelectronics, I look at it when there is an interaction. The name itself says that there is an interaction with light and the matter and the electrons and holes in semiconductor. When we say, we consider as an optoelectronic device, like say could be an optical source where in a semiconductor the electrons and holes recombine, and the balance energy, when electron jumps from conduction band to valence band, it recombines and the balance energy is given in the form of a photon. So it's light. So it's an interaction, light, and both are involved. Means the particles, electron holes, as well as photons are involved. Or you are detecting or sensing the light. Light falls on the semiconductor, it creates electron hole pairs, which you extract in the external circuit, which gives you a current in the external load or a voltage across the external load, and that you consider as a electronic device. Do we call them photonic device? Yes, some books, very good reference books, they will find that they have been referred to as a photonic device. But photonics is something which where you do manipulation with photons, right? So this everything is in the optical domain, right? One of the major application of this optoelectronics or so-called photonics is in the area of optical communication. Optical communication, you had electrical communication, and that has been replaced by optical communication, where the optical that signal which is modulated, the lights which modulates the light, that propagates through optical fiber, and you cover the entire globe with the help of this optical communication. But this is a typical example of an optoelectronic system. Why? Because when you want to communicate between 2 points which are 1,000 kilometers apart, so you cannot do it in one stroke. You'll have to go through taking help of several repeaters. About 30-40 kilometers you have a repeater. So in every repeater, here there's the signal which you want to transmit, say your voice signal. So first you convert it into an electrical signal. Then this electrical signal is used to modulate an optical source. When you modulate this optical source, then this light is transmitted through your optical fiber. And then at the receiver end, you detect that signal. You extract the electrical signal from the variation in the intensity of light and convert back into the electrical signal. Then it feed it to the transducer. Say if it is a loudspeaker, you feed it to a loudspeaker and you get back your voice signal. So this is the way it works. But when you have repeaters, you do this think conversion from electrical domain to optical domain multiple times, right? And that slows down the speed of the system. So when you come to electrical domain, the bandwidth gets limited, right? Optical domain, it's very fast. Electrical domain, it becomes slow. So repeated conversion from electrical to optical domain creates problem. Now, can we create a situation where all this processing can be done in the optical domain without coming back to electrical domain? Electrical domain means again the involvement of electrons and holes will be there, right? Can we avoid it and do all processing? Just for example, my switch will be an optical switch, my gate will be an optical gate, logic gate will be an optical gate, and all processing will be done in the optical domain. So then the first, it will be tremendously fast. So then thus came the concept of optical computation, right? So all these things when you do in the optical domain, and then you can have another type of optical communication, which is coherent optical communication, where we do try to process it in the optical domain. And there are a lot of optical devices like which you call as integrated optics. So all this modulation and everything you can do, processing, everything you can do in the optical domain. And that's truly a photonic system where everything is in the optical domain. You don't come back to the electronic domain. So optoelectronic will be a combination of this. Photonic will be purely in optical domain, which is believed to be very, very fast. So people are looking for this optical communication where you'll never come back to electrical domain and everything will be in the speed of light. And that will be a true optical communication. So the repeated coming back to electrical domain will not be there. Or some researches were going on soliton pulses. If you can develop soliton pulses, they can be transmitted over a long distance. So there will be no intervention of electronic system there. So, and you can travel a very, very large distance in one stroke. So that kind of concept is a true photonic. So when every manipulation you are doing in optical domain is truly a photonic system. And now there are a lot of other advancement also, your quantum photonics, where the individual photons can be manipulated. We are in optical sources, detectors, or modulators. The radiation you are, or stream of photons, you are manipulating that stream of photons, changing the intensity in accordance with some electrical signal, or doing all these kind of manipulations you are doing, which is a stream of photons. But quantum photonics is where individual photons can be manipulated, and that itself has a separate and vast area where people are working in this area. So that's why I said it's a very broad field to have a conference on this. You should have several parallel sessions continuing for this, because the advancement has been tremendous. Phenomenal advancement is in the field of photonics and your optoelectronics, and electronics is already vast area. So I think the speakers will touch upon a few aspects of this. Another thing which you should know that I think Professor Shivashish Bhomik mentioned about these semiconducting polymers. They itself is another field of research which has given birth to flexible electronics or stretchable electronics, right? Where this electronics, the age is coming when you'll be able to fold your mobile in the form of a piece of paper and put it in your pocket, or you can roll your television screen and like your drawing sheet and put it in your car. So this kind of technology is coming, and organic light emitting diode is one of the major invention and commercially successful your technology which is used in the display technology. It is having a huge share of the market today, organic light emitting diodes. So they use organic semiconductors and they give brilliant colors which cannot be matched with by any inorganic materials giving this kind of colors. And many of you may not be knowing that your smartphone you are using actually organic light emitting diodes, and LG and Samsung both are having commercial television screens which are using organic LEDs. These are the new generation materials which have come. The organic polymers, semiconducting polymers. So they have created another area of research. So it's a very vast area. And oxide semiconductors, for example, that itself is another area where different kinds of nanostructures have been tried for electronic application, optoelectronic and photonic applications. Right, many thin film transistors have been developed using this oxide semiconductor. So in 3 days with a limited number of speakers, you cannot cover all the areas, but you will have a glimpse of what is happening around and what is the future trend. And once again, I congratulate the Department of Physics for organizing this webinars on such an important topic, and the participants will definitely learn from their peers in the field, and I wish the program a grand success. Thank you very much.
Thank you very much, sir, for your nice presentation. So you have mentioned briefly about our journey from the vacuum tube diode to the modern day semiconductor materials, which is used for integrations of circuits, and also mentioned about the oxide semiconductors. You have also mentioned about the differences between the photonic and the optoelectronic devices nicely. So thank you very much, sir, for your illuminating presentation. Okay, now we shall move to the technical session. Now that will be started, I think, at 11 a.m. So I conclude this session right here. Thank you very much for being with us in this session. Good morning to all of you.
Thank you, Namaskar.
We shall be back at 11 a.m.
Good.
Good morning to all of you.
Good morning. Good morning, sir. Good morning.
Good morning, good morning. Good morning, Partha. Good morning, Somnath. Good morning, Samir. I'm seeing all of you here.
Good morning. Good morning.
After a very, very long time.
How are you, sir?
I'm fine. I'm fine.
Okay.
So I will press the present now and then switch on my.
Yes.
Okay.
Would you not introduce?
You have to. No. All these
No,
things.
I'm just starting now. I'm just checking.
You have to share your screen, sir.
Yeah, I'm more used to Teams and Zoom. Google Meet, I have not done much.
So here also present. You have to go to the present now option, and from there your PowerPoint or whatever maybe that screen should be there in the screen.
Yeah,
that should be opened in the screen.
Okay, great. Yeah.
Okay. So we are going to start the technical session 1 of our webinar. It's a great opportunity for us that in this session we will be enriched a lot by the talk of the famous personality in the domain of optics, Professor Krishna Tyagarajan, to whom myself along with my students and so many persons present here are indebted a lot for his contribution in the domain of fiber and waveguide optics. This session will be chaired by Professor Partha Raichaudhuri from Department of Physics, IIT Kharagpur. He is working in the area of fiber and integrated optics and photonics. In the year 2000, he did his PhD from IIT Delhi. He then pursued postdoctoral research in the Kyoto Institute of Technology, Japan, as a Japanese government fellow. In 2000, he joined as the faculty of physics department, IIT Kharagpur, where he is currently involved in teaching and research. He has supervised 8 PhD theses. His research is funded by institute and external agencies including DST, DRDO, BRNS of Government of India. He has published more than 90 research papers in various international referred journals and contributed chapters in 6 books and edited volumes. And he is a life member of Indian Optical Society, Institute of Electronics and Telecommunication Engineers, Indian Science Congress Association, and regular member of Optical Society of America. He is also a regular editor and member of the editorial board of Asian Journal of Physics. His current research interests are in the area of microstructured optical fibers, photonic crystal waveguides, and devices. I request Professor Raichaudhuri to chair this session. Please, Professor Raichaudhuri. Please unmute yourself, Professor Raichaudhuri. Please unmute yourself.
Professor Raichaudhuri, your microphone is mute now.
Okay.
Please unmute. Yeah, thank you.
Thank you very much for the nice introduction. I am indeed very proud and privileged to be part of this esteemed conference. But the talk of the session, which I am going to chair, is by my teacher, Professor Krishna Tyagarajan. I am personally indebted to him. I have learned a lot of things from him during my stay in IIT Delhi as a PhD student. I used to meet him, talk to him, and could get solution from for many issues of the research problem. So I am personally very much indebted, and I am very much thankful to see him here. I will be reading out his brief biodata, but that is, he is much more than that, and he is many times beyond that. So Professor Krishna Tyagarajan, he is an eminent personality in the field of optics, optical electronics, fiber and waveguide optics and lasers. At present, he is the head of the department and professor of the Department of Physics under the School of Engineering and Applied Science in Bennett University, Times Group. He has been associated with IIT Delhi for a long time, and is the former professor and HOD of the Department of Physics, IIT Delhi. Professor Tyagarajan is a renowned teacher of physics and has been awarded the Excellence in Teaching by IIT Delhi in 2011. He was an elected fellow of the Indian National Academy of Engineering in 2008 and the Optical Society of America in 2005. He has received the prestigious title of Officers dans l'Ordre des Palmes Academiques by the French government. I don't know whether the pronunciation is right or not. In 2003. He has held visiting positions, many positions, out of that few I'll just name here, at École Normale Supérieure Paris, France, Laboratory Centrale de Recherche, Thomson CSF, France, Department of Electrical Engineering, University of Florida, USA, University of Waterloo, Canada, the City University of Hong Kong, and Tokyo Institute of Technology, Japan. He has published more than 165 research papers in international journals of repute, and he is the co-author with Professor Ajay K. Ghatak of 10 books in the areas of optics, optical electronics, fiber optics, and lasers. These are all very fundamental and very popular books, very useful books for undergraduate and postgraduate levels. In 1998, he was the co-recipient of the Fiber Optic Person of the Year 1997 award by Lucent Technologies, Finolex, and Voice and Data, India. He had been a consultant to Tejas Networks India Private Limited, Bangalore, looking into advanced issues related to high-capacity communication through optical fibers. His current research interests are in the fields of guided wave quantum optics, optical fiber amplifiers, nonlinear optical effects in waveguides. We hope all the researchers, scientists, and technologists present here will be immensely benefited by a talk by his presentation on nonlinear optics, the good, the bad, and the esoteric. With this very brief introduction bio about my teacher, Professor Tyagarajan, I request him to take over the microphone.
Thank you, Partha. Thank you so much for your warm words. I would like to thank Masumi Basu and the Department of Physics for inviting me for this talk. In these times, COVID times, it's very nice to see that the conferences go on, webinars go on, and the interactions keep happening. So let me present my screen, entire screen. Okay. So wait. Can you see my screen?
Not yet.
Do I have to do anything other than that?
No, not yet.
Oh, share. I have to. Okay, no. Why should you say share your entire screen? Share. Wait, cancel. Let me start again. Share entire screen.
Yes.
I'm not getting the option of share. do I have to get permission or something or what? I'm not able to share. It says I can't click on the share.
No, in the small screen, you can see the similar one share is there. You click on that. In the small screen.
Yeah, the small screen, the share is not functional. I'm not able to click on the share.
Within this small screen, you can see the share option. Right? Just click on it.
Which one? I'm not able to find out. I mean, okay, wait. Oh, yeah, okay.
Okay, have you got it? Huh.
Yeah. Can you see the screen now?
Yes, sir.
Yes, it's coming now.
Okay.
Yes.
Okay. So, again, thank you very much for this invitation to give a talk in this webinar series. And so my talk is titled "The Nonlinear Optical Effects: The Good, the Bad, and the Esoteric." So this comes from the title of a famous Western classic movie called "The Good, the Bad, and the Ugly," which was released in 1966. And if I can, I don't know whether I can stop sharing. It's okay. This is a beautiful song which is played in the entire series of the entire movie, and it's a very beautiful movie that was introduced in 1966. Let me stop the playing. Okay. Okay, so I chose the title based on this particular title of the movie, "The Good, the Bad, and the Esoteric." So nonlinear optical effects have good properties of generating new wavelengths, as we will see through the talk. You can convert from one wavelength to another wavelength through interaction through nonlinear optical effects. It affects optical communication system. It generates noise in communication system, and that is the bad part of it. And the light that gets generated by nonlinear effects have some strange properties, and that's why it's called the esoteric. Esoteric means mysterious properties. So I will briefly cover these three aspects of nonlinear optical effects. So that's my talk. The outline is what are nonlinear optical effects, the three primary areas, and then some conclusions. Now, we're all familiar with linear optics, where the polarization generated in the medium is proportional to the electric field that is applied. And this is a electrical susceptibility. And this polarization is nothing but dipole moment per unit volume. So if you plot P versus E, you get a straight line. So if you have an electric field which is sinusoidal with time, it will generate a polarization which is also sinusoidal at the same frequency because of this linear relationship. So the polarization will generate its own electromagnetic field because polarization is nothing but dipoles. So when dipoles oscillate at the frequency omega, then it generates radiation at frequency omega. And that is one of the reasons why light travels a little slowly in media, because the electric field that you're observing is actually a combination of what is entering plus what is generated by this polarization in the medium. Now, what happens is when you increase the electric field strength, and this happened when lasers were invented, that electric fields inside the medium could become very, very strong. In that case, this equation is actually an approximation, and polarization has higher order terms here. So there is a term on proportional to E square, proportional to E cube, and so on. That's a kind of series expansion. These are extremely small quantities, but when the electric fields become strong, then these terms become significant, and these are the nonlinear terms. So nonlinear optics essentially deals with the effects of these terms on the propagation of light through media. So polarization is no more proportional to the electric field. It has nonlinear terms, E square term, E cube term, and so on, and these result in the nonlinear optical interactions. So if you plot P versus E, you don't get a straight line, but a line which is not a straight line. So if you have a sinusoidally oscillating electric field, you will generate polarization at new frequencies, and that is the reason why you can generate new frequencies. So as an example, if I take an electromagnetic wave at frequency omega, and if you look at this term, E square term, the nonlinear term which is proportional to E square, so D is a constant, nonlinear constant here. So if you substitute electric field as cos omega t minus k omega z, k omega is the propagation constant. This is the light wave propagating along z direction. If you substitute here, you will get a cos square term, and cos square theta can be written as 1 plus cos 2 theta, and you get 2 terms here. So the nonlinear polarization in the medium contains a DC term, which is independent of time, and it is a term which is at frequency 2 omega. So although you have applied a frequency omega into the medium, your polarization has a frequency 2 omega. And because polarization is nothing but oscillating dipoles, these dipoles now are also oscillating at frequency 2 omega. And when a dipole oscillates at frequency 2 omega, it will generate radiation at frequency 2 omega. And that is the origin of second harmonic. That means you launch a frequency omega and you get a frequency 2 omega, which is the second harmonic. This term, which is independent of time, is called optical rectification. It creates a DC potential difference between the ends of the crystal. It's not much of significance. I'm not sure whether people have really used this to any applications. So if you take a linear medium, if you shine some color light, it comes out of the same color. There is no change in color. You can get scattering, etc. The color, the wavelength doesn't change at all. But in nonlinear optics, you can take a crystal, launch red light into that, and come out with blue light. So if this is omega frequency, this is 2 omega frequency. And so the frequency gets doubled, or the wavelength gets halved. And so red gets converted to blue. And that's the beauty of nonlinear optics. You can actually convert wavelengths across the spectrum. Now, the polarization, as I mentioned, represents oscillating dipoles. So, and these oscillating dipoles are radiating electromagnetic waves at all in all directions. Now, the problem is that because you have so many dipoles in the medium, you have to ensure that the radiation coming from all these individual dipoles, they all add in phase. Otherwise, you will have destructive interference, which means essentially that you have to satisfy some conditions so that the radiation coming from individual dipoles in the crystal all add constructively. And mathematically, one can show that this leads to what is called as a phase matching condition. That is, the propagation constant of the medium at frequency 2 omega must be twice the propagation constant of the medium at frequency omega. And this is nothing but a condition that the refractive index of the medium must be the same at frequency omega and 2 omega. If you do not satisfy this condition, you will not satisfy phase matching condition, and in that case, the generation efficiency can be extremely poor. So please note that just because you have polarization oscillating, it doesn't mean generation of electromagnetic waves, because the different polarizations coming from different waves coming from different dipoles may not add constructively and may all cancel each other off to get no significant generation of second harmonic. So I have to satisfy this condition, and this is called a phase matching condition. So you can actually understand this process in a quantum mechanical picture. So what is happening in second harmonic generation is 2 photons at frequency omega merge to form a single photon at frequency 2 omega. That's energy conservation. So you have 2 photons in the beam which is coming into the medium through the nonlinear medium. The nonlinear medium helps in merging or fusing 2 photons at frequency omega to form a single photon at frequency 2 omega. Now, if you consider this as a picture in terms of particles, you know that this process has also to conserve momentum. So the 2 photons have momenta h cross k omega each of them, and the momentum of the generated photon is h cross times k2 omega. And to satisfy phase matching, you can see that the sum of these 2 vectors must be equal to this vector, which is actually nothing but the phase matching condition. So phase matching condition comes from Maxwell's equations through simply putting the condition for constructive interference, or from a quantum picture in terms of essentially the fact that it's the momentum conservation condition required for fusion of the 2 photons into a single photon. Now, if you were to calculate efficiency as a function of position, as a function of length, as the wave propagates through the crystal, the second harmonic gets generated. Now, if you do not satisfy phase matching, you can see that the efficiency is extremely poor. So there is a slight generation and then it comes back and so on. This is exactly like trying to couple with energy between 2 mechanical systems like pendulums. where the time periods are very different. You may be having coupling, but no energy transfer. If you satisfy phase matching, the efficiency increases quadratically with length. So this shows the importance of phase matching in this interaction process. The problem is, how do you achieve this condition? Because all media possess dispersion. That means the refractive index depends on frequency. And so to satisfy this condition is not obvious. So one condition which is conventionally used is called birefringence phase matching, where you use the birefringence property of the medium to satisfy this condition. So you can use the ordinary and extraordinary waves to satisfy this kind of condition. But there is a more interesting technique which was proposed by Bloombergen in 1961 that is called quasi-phase matching. So what you do is you periodically reverse the sign of the nonlinear coefficient along the propagation direction. So this arrow represents the optic axis of the crystal, uniaxial crystal. So optic axis pointing up, then down, then pointing up, down, periodically with a period lambda. Now, this periodic variation actually corresponds to a momentum, capital K, 2 pi by the period. So what you can do is you can use this X. So if you have 2 omega propagation vector here, then the omega propagation vector, they're not equal. 2 times k omega is not equal to k2 omega, but you can compensate by having an additional k vector, which is the periodic because of periodicity. And please remember now that because this periodicity, I can manipulate myself. I can change the length of this capital K vector and hence achieve phase matching irrespective of the crystal. And so this is a photograph of an etched crystal from the top. These the etching rates for optic axis pointing up and down are slightly different. So you can see these patterns. So this is one pointing up, this is pointing down, this is pointing up, this is pointing down, and so on. So there are periodic variations, and these periods could be of the order of few microns. So this is called a periodically poled crystal, and these are now commercially available, and this technology is extremely well advanced now. So if you were to look at the same problem again, a phase matched efficiency goes up very fast. A non-phase matched operation never rises up, but a quasi-phase match, this is called quasi-phase matching, it rises up, but not as fast as phase matching, but at the same time, it just go up. So the current technology of nonlinear optical interactions mainly use quasi-phase matching wherever possible, because you have you can engineer the process to achieve phase matching for any combination of frequencies. So this quasi-phase matching is a very important technique, which actually got implemented in the 1980s, and you can actually today commercially buy quasi-phase match crystals. So you can actually generate crystals in which you have multiple periods. This is one period here, is another period here. So you can launch a single wavelength and generate all 3 primary colors. That's beautiful because you can actually use this for white light screens, for example. So you don't have to have 3 lasers. You can start with a single laser. You have a domain engineered crystal here. It's called domain engineering, and you can generate all the 3 primary colors that is required. So there is a very interesting possibility. A lot of interesting possibilities exist with this particular technology. Now the question arises that suppose because I just now saw that if I launch red light into a crystal, I can generate blue light. So obvious question is, can I reverse this process? Can I launch blue light and generate red light? Now, when I go back and look at Maxwell's equations and try to analyze, I say this is not possible. That means Maxwell's equations, classical electromagnetism does not allow the 2 omega frequency to get converted to omega frequency. It predicts omega to 2 omega conversion process, but it does not predict a 2 omega to omega conversion process. But when I do an experiment in the lab, I find red coming out of blue. And there is no classical explanation for this. This is a completely quantum mechanical process. This process requires quantum mechanical explanation. And what is actually happening is, if one photon at 2 omega splits into a pair of photons at omega, it is just exactly the reverse process. The second harmonic is a fusion of 2 photons into a single photon. The reverse process is called subharmonic generation or down conversion process. Is 1 photon at 2 omega splitting into 2 photons at omega. And so for every photon that you've launched here, if it splits, it gives you 2 photons here. And these 2 photons are daughter photons of the single photon. And because they have been generated through a single photon here, these photons have very, very interesting properties, which are the mysterious properties, which I'll come to a little later towards the end of my talk. So this is a process which is classically prohibited, but happens in nature, and nature completely quantum mechanical description. Now, before I go to this process, there is another process which is a similar process in which you launch both the 2 omega and omega simultaneously, and classical electromagnetism shows that this particular process can amplify this red light. That means you launch a blue light and a red light simultaneously, very weak red light, a strong blue light, and you can amplify the red light. So this is a classically allowed picture. Classically not allowed picture is this one where there is no omega incident. See here, there is a difference. There is only 2 omega coming in, omega gets generated. Here, both omega and 2 omega are coming in, and omega gets amplified. So this is called a parametric amplifier, and the parametric amplifiers are very well used in microwaves and other areas. So this is a process in which it's called optical parametric amplification, where you launch one frequency 2 omega, one lighted frequency 2 omega, another lighted frequency omega, which is half of this, and you can amplify this. Now, parametric amplifiers are not new. They are quite old. Michael Faraday did a lot of experiments in 1831. So he showed that if you take a wine glass and move your hands around the glass, the wine starts to vibrate. And that's actually a parametric process. Many of these experiments, some of the students may have conducted this experiment in college. It's a very interesting, beautiful experiment. And you can actually excite a string, a natural frequency of vibration by twice the frequency. And Lord Rayleigh analyzed this in 1883 to 1887. And a classic example is a child on a swing. So here, what does the child do? The child sits in the first quarter, stands in the second quarter, sits back in the third quarter, and rises up in the fourth quarter. So what the child is doing is it is sitting for the first quarter down, coming down, then stands while going up, then sits while coming down, and stands while going up. So in one cycle of the pendulum, one cycle of the swing, the child has done 2 sittings and standings. So the child is pumping the swing, which has a frequency omega, by sitting and standing at frequency 2 omega. And that's a very, very interesting example of a parametric amplifier. The child is sitting and standing, and the child is doing work on the swing. And by sitting and standing, and that work is getting converted to increased amplitude of the swing. Now, if there is no one to stop the child's swing, and the child wants to reduce the amplitude, what the child has to do is to sit and stand at the wrong times. So it stands while coming down, sits while going up, stands again while coming down, sits while going up. So if you pump the swing at the wrong phase, you will decrease the amplitude. If you pump at the right phase, you increase the amplitude. If you sit and stand at the wrong phase, you will decrease the amplitude. So this is a very classic example of a phase-sensitive amplifier. Depending on the phase at which you are sitting and standing, the swing will get either amplified or de-amplified. And this is a characteristic of all parametric amplifiers. So depending on the phase of the sitting and standing by the child, you can either amplify the swing or attenuate the swing. Also, please note that if there is no one to push, how would you start the swing? So you sort of shake the swing and you pick up the right phase to sit and stand, and the swing will start to amplify on itself by exactly picking up the right phase. So you see, what you're doing is you can actually start from noise and amplify your signal of the appropriate phase. The appropriate phase signal gets amplified of the noise. So it's a very interesting example of a parametric amplifier. And so optical parametric amplifier essentially deal with this following. So you have a strong frequency at 2 omega and a weak frequency at omega. So this is the frequency of the sitting and standing, which is called the pump, which is actually pumping the energy. And this is the frequency of the pendulum. And so you are actually amplifying the pendulum's amplitude. That means you are amplifying red. So this is a very interesting example. And because of this phase-sensitive nature, which I will mention towards the end of my talk, the amplifier, phase-sensitive parametric amplifier, has much lower noise characteristics. They are much better. They have much better noise characteristics compared to the standard erbium broad fiber amplifiers. So here is a classic example of some work done in 2018. You can see that the transmission distance that is possible using EDFA, the erbium broad fiber amplifier, which is called phase insensitive amplifier, is typically about 800 kilometers. And by using phase sensitive amplifiers, phase sensitive parametric amplifiers, the distance has been increased to 4,500 kilometers. What has happened is the amplifiers which are periodically amplifying the signals, they keep on adding noise. So EDFA's noise is so large that after 800 kilometers, you have to regenerate the signal, regeneration. But if you use parametric amplifiers, you can actually go much beyond, about a factor of 7 or 8 of this frequency, of the distance, and you can go to very, very large distances. So parametric amplifiers essentially use the nonlinear optical property of the crystal for amplification process. At IIT Delhi, we have been doing some work for some time. Some of my graduate students have done. We have tried to look at problems for increasing the bandwidth of the second harmonic process, or using simultaneously second harmonic generation and some frequency generation. So we have done some interesting work in this area using optical waveguides, and all this essentially involves the classical picture of electromagnetism and using nonlinear optics. Now let me come to the bad part of my nonlinear effects. So this involves optical fiber communication. A very brief introduction here. So optical fibers are cylindrical structures made of glass. You have a core and a cladding. The core has a slightly higher refractive index than the cladding, and the radius is typically 10 to 50 microns here. Single mode fibers have about 10 micron diameter, multi-mode fibers 50 micron diameter, and it's made of silica. As was mentioned, it's one of the most abundant materials on Earth. And that's a 25 kilometer long fiber carrying green light, and the light you see is because of Rayleigh scattering, the same mechanism which is the reason for the blue sky. So a typical fiber optic communication system, today's system, is called a wavelength division multiplex system. So you have, say, maybe 80 different wavelengths. Each wavelength is carrying its own signal. They're all multiplexed into a single output, then amplified, and then it goes through a link, maybe 80 kilometers long, and then amplified, another 80. So there are compensators which compensate for dispersion and so on. So you go all this distance, about 600 kilometers. Now this limit comes in because of the noise by these amplifiers. You have to regenerate the signal. And at the end, you demultiplex them into the channels, and you can get capacities of terabits per second. Even today, people are talking about petabits per second, 10 to 15 bits per second communication systems. So one thing to notice is that there are n different wavelengths coming through the fiber, same single fiber carrying multiple wavelengths. So if each of them carries 10 milliwatts, and if you have 80 wavelengths, you have 800 milliwatts of power inside, huge power inside the fiber, that optical power that it's carrying. Now, if you take a fiber and take about 100 milliwatts of power into the fiber core, the area of the beam is about 50 microns square, and intensity becomes 2 billion watts per square meter, power per unit area. That's huge. The electric fields of these intense beams are very, very strong, and so the fiber starts to behave nonlinearly. That means the nonlinear effects start to become important, and the least square E cube term become important. Now it so happens, okay, so there are some very important effects that take place. Self-phase modulation, cross-phase modulation, four-way mixing, stimulated Raman scattering, stimulated Bulma scattering, all these are nonlinear effects that take place in fibers, primarily because of the huge power that is present inside the fiber. Now, let me go back to the expression for the polarization. That's a linear term, that's an E squared term, and that's an E cube term. Now, one can show that if you have a medium which has a center of inversion symmetry, then this particular term is absent. That means media which possesses center of inversion symmetry, crystals or random media or amorphous media do not possess this effect, because this requires absence of a center of inversion symmetry. So optical fibers are made of silica, which is amorphous, and so this term is not present. Silica fibers, the first nonlinear term, this is the linear, and the nonlinear term is this one, E cube term. And this is present in all media. And that's the third order susceptibility, chi3. And so what is the effect of E cube term? So polarization becomes linear plus E cube, nonlinear. Now, remember I said that in a communication system, there are multiple frequencies propagating simultaneously. So let me assume 3 channels, omega-1 frequency, omega-2 frequency, and omega-3 frequency. Those three waves are simultaneously propagated through the optical fiber. If you substitute this E into this expression, you will have a cos omega-1 t plus cos omega-2 t plus cos omega-t3 whole cube. So if you have a plus b plus c whole cube, you have a cube, b cube, c cube, then you have a square b, ab square, abc, all kinds of terms. And what you will find is, suppose you have, for example, cos square omega-1 into cos omega-2. So you can write this as a combination of frequencies, and you will find that this polarization now contains many new frequencies. Omega-1 plus minus omega-2 plus minus omega-3. There are a huge number of frequencies that get generated in the polarization. That means the dipoles are now oscillating. Although you have launched 3 frequencies, the dipoles are oscillating now in a linear combination of these 3 frequencies plus a large number of other frequencies because of this nonlinear term. Now, these nonlinear terms in the polarization imply that the dipoles are oscillating at these new frequencies, and these new oscillations will generate their own electromagnetic waves. And this is precisely why you get self-phase modulation, cross-phase modulation, four-way mixing, and all these terms. Simply because when you substitute this into this equation, you get multiple terms. Now, one thing which I want to talk, which is the problem today, is four-way mixing. So if you launch 3 frequencies, as I said, you will generate all kinds of combinations, and one of the frequencies happens to be, for example, nu1 plus nu2 minus nu3. Now, please remember, these frequencies are very close to each other. So you have 1550 nanometer, 1550.5 nanometer, 1551 nanometer. The wavelengths are very close, frequencies are very close. So this nu1 plus nu2 minus nu3 is also very close, because nu2 is approximately equal to nu3. So nu4 is approximately nu1. So if I've drawn in the figure a new frequency generated, which is nu1 plus nu2 minus nu3. So what happens now? So because of these 3 frequencies, you have a 4th frequency. Suppose somebody wants to communicate at the 4th frequency in the system, nu4, he will find crosstalk, which means that the signal at these 3 frequencies will generate some signal at nu4 and will interfere with the signal that is passing at nu4 frequency. So this is called four-way mixing, because you have 4 different frequencies which are mixing with each other to create through the nonlinear optical effects. So obviously this is not good, because suppose I had 4 people, 4 different channels propagating through the fiber, each one of them gets modulated or creates noise from the other 3 frequencies present in the fiber, and that's not good for a system. So I want to reduce this four-way mixing or cancel it completely. Now, before I go to that four-way mixing problem, I must mention that there is a phenomenon called dispersion that takes place. Dispersion is essentially a wavelength dependence of refractive index of a medium. So if you launch a pulse of light into a medium like glass, what you find is different frequencies present in the pulse propagate at different speeds, because the refractive index is different. So what happens is the pulse gets broadened. So if you may launch a 1 nanosecond pulse here, but you may get out with 5 nanoseconds or 10 nanosecond pulse coming out. And this is not good, because if you want to send a second pulse nearby, they will start to overlap at the output, and this creates problem in communication. And this particular, how much of broadening takes place depends on the wavelength dependence of n. And it so happens, okay, so here's the figure. So you have 3 wavelengths simultaneously launched in the fiber. They all come out at different times. The blue one is traveling faster, the red one is traveling slower, so the pulse gets spread out. And such a pulse has blue in the front and red in the back, and this is called a chirp pulse. The pulse is chirped. That means the frequency within the pulse is not constant, and this is called a chirp pulse. Now, it so happens that the amount of broadening depends on the second derivative of refractive index with wavelength. Second derivative. So if the second derivative happens to be 0, then this dispersion will be very, very small or negligibly small. So if you want to have low dispersion or very low dispersion, you have to choose a wavelength for which this second derivative of the refractive index versus wavelength becomes 0. Now, ineffective I'm writing because these are waveguides. Optical fibers are waveguides, and so I must use the corresponding propagation constant in the waveguide. So in optical fibers made of silica, the dispersion as a function of wavelength crosses 0 around 1550 nanometer. Actually, you can make it cross 0 anywhere from 1310 to 1600 nanometer, depending on the kind of fiber you make. You can choose the diameter of the fiber, you can choose the refractive index variation, and control the dispersion. Control this where this becomes 0. And so you can make a fiber which is called dispersion shifted fiber, where the dispersion becomes 0 here. Now, remember, in second harmonic, I was mentioning about phase matching condition. If you want to maximize this process, of four-wave mixing, you must choose 0 dispersion. So, if you choose this point of operation in optical fiber communication system, you will have very low dispersion, but very strong four-wave mixing. Because the condition for four-wave mixing, the efficient condition for four-wave mixing is nothing but 0 dispersion. So these are two contradictory requirements. If you want to avoid four-wave mixing, you should have non-zero dispersion. If you have to have very low pulse dispersion, you have to have 0 dispersion. So these are two contradictory requirements, and that is the result that is. So if you want to avoid four-wave mixing, I should not operate at this wavelength. I must move away from this wavelength for operation. So here is a classic result which was published in 1997. You can see 4 wavelengths were put into a fiber, 25 kilometer long fiber, and this is the output. You can see so many different wavelengths have come out through the four-wave mixing process. This is a dispersion, 0 dispersion fiber. If you take a fiber which has a finite but small dispersion, say 50 kilometers long, no four-wave mixing. So you get four-wave mixing if your dispersion is 0. You will completely eliminate four-wave mixing if you choose a fiber with a finite dispersion coefficient. And so to maximize information, you look for 0 dispersion. If the fiber operates at 0 dispersion, then four-wave mixing is a major issue. So you generate what are called as non-zero dispersion shifted fibers. So today in communication systems, most fibers which are used have a small but finite amount of dispersion to reduce this four-wave mixing effects. But so the question is, what is the ultimate capacity of optical fiber communication system that I can ever have? It's limited by nonlinear effects. The ultimate capacity, can I go to say 1000 terabit per second? Can I go to a million terabit per second, and so on? These limits are coming from nonlinear optical effects. And so this is something that nonlinear optical effects have a problem in optical communication system. And so one has to worry about this. Now I come to the most interesting and the mysterious part, the esoteric part. So basically, Maxwell's equations describe electromagnetic waves as the electric field as a function of position and time, and that's an expression for a wave propagating in the z direction. So classically, a light wave is described by electric and magnetic fields with well-defined amplitude and phase. You can define E0 precisely, you can define phi precisely. And a light wave at frequency omega can have any energy, no restriction. But this classical picture is unable to explain many of the observations. One of them, which I showed you, which I mentioned, was 2 omega getting converted to omega. It has no classical explanation, but the quantum formalism explains all experimentally observed features. And what is this quantum picture? So I have to what we call as quantization of Maxwell's equations. So what it shows is that the electromagnetic energy of a mode at frequency omega, mode means you have a wave propagating in the z direction at frequency omega, which is horizontally polarized, for example. So each mode of frequency omega has only energy which must be integral n plus half into h cross omega. Omega is the frequency of the light. So the energy of the electromagnetic field can only increase or decrease in multiples of h cross omega. So if your energy is say 100 plus half h cross omega, I will say that there are 100 photons in the field. If it is a million plus half h cross omega, I will say that there are million photons in the field. It's just this number n. This is not the number of photons. Please note that even if you have no photon, n is equal to 0, you still have half h cross omega, which is called the 0-point energy, which all of you must be familiar as a problem in harmonic oscillator. You can have, in principle, you can have a field with no photons in any field, in any mode. That means there is no light. It's called radiation vacuum. Even then it has energy. You can never come to a state with zero electromagnetic energy, exactly like you can never come to a state where a harmonic oscillator comes to absolute rest. Because if it comes to absolute rest, you know its position and momentum precisely, and that's not permissible. And in this picture, a photon is just a quantum of excitation of the electromagnetic field. One has to be very, very careful in using the term photon, because there is a normal understanding that photon means a particle like a bullet going. It's a very, very tricky concept, because a photon can be of infinite length, a photon can be of finite length, a photon can be a spherical wave, a photon can be a plane wave. You can have all kinds of possibilities. So all that we have done is we have just quantized the field and we got an excitation of the field. So when I say I have 100 photons in my field, I only mean that I have 100 plus half h cross omega in the electromagnetic field. Now, this picture is a very, very brief mention I have done, but this picture allows some very interesting states of light, which are called single mode states, single photon states, superposition states, squeeze states, entangled states. So there is an entire field of quantum optics which deals with many of these states. And I must mention, there are still many unexplored states of light. There is a huge field in front where still need exploration by the younger people who are in the audience to look at some possibilities of some of these unexplored states of light, very interesting states of light. So I'll just go through some of them. Okay, so remember I said that if I launch 2 omega, I get omega coming out. So what is actually happening is, as I mentioned in this here, I can never have a situation where there is no field at any frequency omega. So in quantum picture, when you are launching 2 omega into the crystal, you are also having input of what we call as vacuum. That means there is nothing. What I call as nothing in classical physics is actually vacuum in quantum physics. So that means something is entering, which is half h cross omega. So what happens is, this particular crystal, these two mix together to generate the omega frequency at the output. So there is a semi-classical explanation where you artificially introduce omega into the crystal and generate, but a quantum picture doesn't need the input here. It clearly shows the generation of omega frequency. Now, it so happens that the omega frequency that comes out is quite different from what was there before the crystal. So, for example, if I take if I have a system in which I have no field at frequency omega, and I try to measure the electromagnetic field, I will get noise. So the noise is completely random, as you can see. The field can never be zero. It's always fluctuating field. It's called vacuum. Now, what is coming out of this is called squeezed vacuum. You see here, the noise increases and decreases periodically. At these times where I'm putting my cursor, the noise is less than vacuum at the expense of increased noise at other times. So it's called squeezed vacuum because I'm squeezing vacuum into a smaller noise level here at these times. So this is very interesting, because if I can make a measurement only at these times, synchronous with these times, the noise in my system is less than what it would have been with vacuum. So this particular understanding results in very interesting applications in increasing sensitivity of interferometers and primarily gravitational wave detection, for example. So if I compare two interferometers, this is called a Mach-Zehnder interferometer. So I have light coming from here, split into a reflected and transmitted arm. They are reflected back into another beam splitter and combined. And if you put a sample here, so the phase difference of this arm can be changed with respect to this arm, and the interference can be changed. And that can be used to measure how the refractive index of the sample changes with temperature or pressure, for example, etc., etc. Very, very sensitive instrument. So here I put nothing. Now, please remember, when I say nothing in quantum physics, there is vacuum entering. Now, instead of vacuum, if I put squeezed vacuum, this particular state here, I can show that the sensitivity is much better because here I have less noise than what is coming here. So this particular interferometer with squeezed vacuum inside inputting into this is much more sensitive to this, and this is what is used, will be used in the gravitational wave interferometer, LIGO. So laser interferometer gravitational wave observatory. This is, I'm sure all of you know about this. This is just measuring ripples. It's 1 part in this 10 to the power 21 or something like that. It's a huge, huge number. And this is an amazing feat of technology, engineering, science, engineering, and technology that you can measure. It's like measuring the distance from the Earth to the sun to an accuracy of the size of a hydrogen atom. That's this accuracy. So there are this kilometer-long Michelson interferometer, and squeezed light at the interferometer is shown to reduce the noise by 28%. So the next generation of LIGOs which are coming up are going to use this kind of sources to increase the sensitivity. And as you also know, that there is LIGO coming up in India, and it should be ready by 2025, somewhere in Maharashtra. So these will require a lot of people with a good background in physics, engineering, mechanical, electrical, materials, etc., etc. So there's a lot of chance, there's a lot of prospect for the younger generation of students to launch themselves into some of these very interesting applications. Okay, now, so this process, if you launch one frequency and you come out to 2 omega frequency photons, depends, which is called spontaneous parametric down conversion. It's a spontaneous process like spontaneous emission. It's a down conversion because the frequency is getting reduced, and it's called parametric because it's a parametric process, exactly like the swing. Now, by appropriately choosing this periodic reversal of domains, you can have a horizontally polarized blue photon splitting into a horizontally polarized green photon, and a vertically polarized red photon. Now, this depends on the property of the crystal, the direction of propagation, etc. This is a classically known phenomenon. So I'm actually satisfying phase matching condition for a horizontal polarization splitting into a horizontal green and a vertical red. I'm just drawing 2 colors just to show different frequencies. So the frequency of this input photon is equal to the sum of the 2 frequencies, energy conservation and momentum conservation because of this periodic reversal. Now, if I change the period of this back and forth, up and down modulation, I can change from horizontal green, vertical red to horizontal red, vertical green. So all photons which are coming out here at the red wavelengths are all vertical. All photons coming out from here and the green wavelengths are horizontal. Here, all photons coming out from the crystal are red, green are vertical, and red are horizontal. So these are 2 orthogonal processes. You can see here, horizontal green, vertical red, horizontal red, vertical green. Now, if you can actually domain engineer the crystal so that both these processes can happen at the same time. So I have a crystal in which both these are there. I can, what's called domain engineering. So this blue photon has a equal probability of splitting into horizontal red, vertical green, or horizontal green, vertical red. So it's like saying that if you have a double slit experiment with a single photon, the photon can either pass through the upper hole or the lower hole. You don't know which one it has come out through to get the interference pattern. Exactly similarly, which process has taken place, you have no idea, but you're getting 2 photons. They can be either horizontal red, vertical green, or horizontal green, vertical red. So this pair of photons which are coming out are called polarization entangled photons. So these have a very strange property, and I will explain what is the meaning of this strange property. So I do the following experiment. So I come with this pair of photons. I have a beam splitter, which reflects all green light and transmits all red light. So all the green photons are reflected, all the red photons are transmitted. Now what I do is, I put a polarizer here at 45 degrees and this one at -45. So these 2 are orthogonal to each other. So the green ones are coming here. So remember, photons cannot be split. So a photon will either pass through the polarizer or not pass through the polarizer. So whenever the green photon passes through, I call it 1. Whenever the green photon does not pass through, I call it 0. So I will measure in the detector a random bit sequence, 1, 1, 0, 1, 0, whatever, that's a particular sequence of numbers. That means green photon passed, then did not pass, passed, did not pass, passed, did not pass, did not pass. It's like coin toss. Similarly, the red photon also does the same thing. But curiously, this sequence of random numbers is exactly the same as the sequence of random numbers. These are two orthogonally oriented polarizers. So I said, no, okay, now let me change the orientation. I choose this at 60 and 150. Again, 90-degree difference. I get another random pair. Random number here, another random number, identical. The green photon has 50% certain chance of going through randomly. The red photon has a certain chance of going through. But it seems to be that whenever the green photon passes through, creating a 1 here, the red photon has also passed through to get a 1 here. Both these processes are completely random, but completely correlated. I change the angle, 120 and 30. Again, perfect correlation. So it seems that a measurement of the polarization state of one of these photons immediately defines the polarization state of the other photon. So measurement of state of polarization of each photon is completely random results. In fact, you can show the polarization state of the two photons are not defined prior to the measurement. Prior to measurement, there is no definition. The two measurements are completely correlated no matter what orthogonal pair of orientations I choose. Measuring the polarization state of one of the photons immediately defines the state of polarization of the entangled photon irrespective of their physical separation. Please note that there is no requirement of these to be in the same lab. They can be millions of miles away. Still, it is happening. So this particular pair of photons which are coming out, these are called entangled photon pairs. These are very much useful in quantum computation, cryptography, teleportation, quantum sensors, quantum radars, and so on. There's a lot of technology now, quantum information science and technology, which has become very important. In fact, there are commercially available devices, quantum key distribution from a company in Switzerland and some companies in the US. So you can use these devices. These are using quantum mechanics to encrypt messages which can be completely secure. China has launched a satellite called Mischius about 500 kilometers from the Earth, and that satellite is communicating entangled photon pairs, one to China and one to Austria, and they're doing measurements, and they are absolutely satisfying all the requirements. And so possibly in the near future, you'll have a quantum internet where it's completely unhackable internet. There are people now working on integrating many of these components into a single chip. This is a silicon chip which has 550 optical components, and it does a quantum computation process. These kind of devices should become available for quantum computation. So essentially using the quantum properties of light to generate light of certain properties which are classically not available, and to do measurements. So there's a lot of money being spent across the globe. $1 billion in Europe, quantum technologies, USA, major companies are working on it. China, of course, is one of the leading members here. And India, you may remember, last year, the finance minister has announced 8,000 crore rupees budget to support quantum technologies. And there's a number of groups in India who are now working on quantum technologies. And very, very important to see that India will not hopefully lag behind in this. I would like to end by a very interesting observation that we normally imagine the classical world to be made up of real stuff, existing in space and changing only through local interactions. So we know that there is a sun here, there is moon here, there are tables, there are chairs. But quantum mechanics says this picture is false. Particles have no positions and no momenta. When you observe them, you create a position and a momentum for that particle. And that is why in quantum physics, measurements cause disturbances. If you compare this with our philosophy, Vedanta philosophy, Vedanta says that the cosmos comes into view simultaneously with him who sees it, and there is no detailed process of creation. It is similar to a dream where he who dreams simultaneously, the dreamer comes with the dream that he's experiencing. It's a very interesting analogy. There are a lot of physics people who work in quantum physics looking at the similarities and comparisons between what our forefathers long time back had actually envisaged. So I would like to summarize my talk. Nonlinear optics leads to new frequencies. You can use them for good effects for generating all kinds of new frequencies, optical parametric amplification, which are technologically very important. It leads to cross-talking communication systems, and that is a problem that one has to keep track of. It has many mysterious properties, generating entangled photons and squeeze states and so on. So nonlinear optics is expected to play a very significant role in the future technology of quantum information science. And thank you very much for your patient listening. And I will be willing to answer any question that any of you may have. Thank you. So shall I stop presenting?
There are few questions received from the chat box.
Okay,
I don't know whether they can directly ask you the questions or I can just read out. These are simple.
Hello.
One question is,
hello.
Please go ahead.
Hello.
Ask the question. Yeah, hello.
Hello. May I ask a question? I am Dr. Sampad Mukherjee from IIEST Department of Physics.
Sure. Please go ahead.
So, my question is that is there any phenomena related to the lattice vibrations in your process of dispersion or all these things?
That lattice vibration, lattice vibration actually leads to Brillouin scattering. Raman and Brillouin scattering, similar to Raman and similar to Brillouin scattering, are coming from optical phonons and acoustic phonons. But this process, this nonlinear second harmonic generation doesn't use the lattice at all. It is electronic transitions, electronic vibrations of the dipole.
My second question.
Yeah, go ahead.
Go ahead, Shampadda.
Please ask the second question.
Maybe some technical problem.
Yes. Is there any other question?
There are questions in the chat box.
I can read out.
Some of those questions are forwarded from the YouTube channel, live streaming.
Oh, okay. Okay, there are questions. Let me go backwards. Vijay Krishna Ghosh, is there any particular arrangement in the grating-like structure for getting a specific type of green and red output? Yes. So you have to choose an appropriate period of the grating structure to satisfy the quasi-phase matching condition, because you need to the grating spatial frequency of the grating must match the propagation constant difference between the omega and 2 omega frequencies. So there is a particular arrangement. There is a field called domain engineering where you can actually modify, you can make it fanned gratings, you can make it chirped gratings, and all kinds of gratings. So yes, there is a specific arrangement that you need to worry about. Vijay Krishna course, what should be the minimum dispersions? Partho?
There is another question that what should be the minimum dispersion so that one can neglect the effect of this FWM?
Actually it depends on the condition you put. If you want crosstalk less than 40 dB, then you might say 2 to 3 picosecond per kilometer nanometer should be sufficient. But if you want a much deeper reduced four-way mixing, then you have to have a slightly higher dispersion. So the closer the dispersion is to zero value, the higher the four-way mixing probability. So it will depend on what kind of limits you are putting. So typically 2 to 3 picosecond per kilometer nanometer is sufficient to reduce the four-way mixing issues to below the required levels of crosstalk. There is another question. As we told, many different frequencies may be generated from the three input frequencies. Why are we considering only 4 at the input as four-way mixing? Okay, so there are many frequencies can be generated. So as I was mentioning, you need to satisfy phase matching conditions for the generation of the frequencies. So if you are able to satisfy phase matching for multiple frequencies, then you will generate all of them. First part. Second part is many of those frequencies are far away. For example, nu1 plus nu2 plus nu3 is very different frequency compared to nu1 plus nu2 minus nu3. So there are many frequencies, but only some of them will be generated because you will not be able to satisfy phase matching condition for all of them. And some of them are very far away. So I don't care about those frequencies, whether they are there.
Correct. It should be comparable.
Yeah, it should be comparable. Then Vijay Krishna Ghosh, how to generate 3 colors using one wavelength. Okay, so the what is actually happening is multiple processes are taking place. Parametric down conversion and mixing of light between what you have launched and the down converted light and so on. So that slide shows that there are some different frequency and parametric processes all taking place simultaneously to generate multiple frequencies in the output, 3 primary colors. Yeah, that's all I think.
So there is one curiosity for myself.
Yeah.
That is slide 46, when we were comparing this 0 point energy with the quantum mechanical harmonic oscillator, harmonic oscillator problem. So in absence of any radiation in the state, there is a frequency half H line omega, half H cross omega.
Yeah.
What frequency does it correspond to? Because there is nothing.
Any frequency?
Oh, you take continuum.
Continue. So any frequency you pick up, you will find noise.
I have one question, please.
One second, Somnath. So is that clear?
Yes.
See, you generate any frequency you take, you will find some noise there, which is half H cross, which is the 0 point. They're called 0 point fluctuations. So if you do an experiment to measure the current at any frequency, you will find finite. If you detect any frequency with no light, you will still get a signal, noise. It's called vacuum noise.
I see. So that corresponds to that 0 point energy.
Yes, 0 point fluctuation. 0 point fluctuation. Yeah. Actually, that 0 point fluctuation is what is responsible for spontaneous emission. Because in quantum mechanics, the higher excited state is an eigenstate of the atom. So why should the atom jump from the excited state to the ground state? That is brought about by the spontaneous emission, is brought about by the 0 point fluctuation that is present everywhere.
Oh, yes.
Yeah. Yes, Somnath.
Excuse me, sir.
How? Very nice and scintillating lecture, but I like to know how all your concepts lead to help the supercontinuum generation, which is also much talked. Supercontinuum generation.
Yeah. So actually, if you have a very strong light in an optical fiber, a Chi3 nonlinear medium, you can have multiple processes simultaneously taking place. Stimulated Raman scattering and the third harmonic generation, multiple frequency generation. So it actually generates a continuous band of frequencies over maybe 1 octave or something like that. So it is multiple nonlinear processes simultaneously taking place in the optical fiber, which is lead to a supercontinuum generation.
But you can technically manipulate that thing in a coherent fashion and
yes. In principle, by modulating the dispersion of the fiber. For example, so photonic crystal fibers are currently being used for supercontinuum generation because the nonlinearities are much stronger, because you can confine the light to a much smaller cross-sectional area, and that leads to a much higher intensity levels for a given power. And so you can control the dispersion property of the medium and generate supercontinuum generation.
Okay, thank you.
Excuse me, sir.
Yeah.
I am Dr. Hiranmay Mahapatra from C.V. Raman Global University, Odisha.
Yeah.
So I have a question actually. Is there any possibility to reduce intramodal dispersion?
Intramodal dispersion?
Even if we are using multimode fibers.
Yeah, by graded index fibers. You see, if you take there are optimized profile fibers. You may have studied in fiber optics course. If you take a step index fiber, it has a large dispersion, 15 nanosecond per kilometer or so. If you take a parabolic index fiber, a fiber in which the refractive index profile is parabolic, you can reduce the dispersion significantly by a factor of 100 or so.
Yeah.
If you go to an optimized profile, so it is 2 minus 2 delta, the coefficient, the exponent, you can reduce it even further. but finally you will be limited by waveguide dispersion and material dispersion of the BD.
Yes.
So you cannot eliminate the intermodal dispersion completely. But what people can do is to pick up excitation of only groups of modes which have zero intermodal dispersion.
I'm asking about intramodal, not intermodal.
Intramodal. Oh, intramodal. Yeah. So intramodal depends on material and waveguide dispersion.
Yes.
So material is fixed by silica. You can't do anything with that. But intramodal, by the waveguide dispersion, you can modify by changing the waveguide parameters, the core radius, the core refractive index difference. And you can have zero intramodal dispersion at any wavelength of your choice, say from 1300 nanometers to 1600 nanometers or so. So the single mode fibers have only intramodal dispersion.
Yes, I know that. If we use multimode fiber, how to reduce it? There is no possibility. Multimode
fibers, the intermodal dispersion is so strong, I don't worry about intramodal dispersion, except material dispersion. You see, so multimode fibers will have intermodal dispersion, material dispersion, and waveguide dispersion.
Yes.
So I will only worry about intermodal dispersion and material dispersion, and not worry about waveguide dispersion, because waveguide dispersion is very small.
Okay, sir. Thank you, sir.
And I may be able to do that for one or two modes, maybe a few modes, but not all modes. It's not possible. I don't think it's possible.
Thank you, sir.
Thank you.
Okay. If there is no more question,
I have a question.
Then, okay, please.
I have a question.
Please. Yeah.
Okay. You said something about Bell. I think, okay, it's not an entangled state. Okay.
Yeah.
Now, is it possible to check the Bell inequality? That means you now it is the general idea is that the entanglement is real, and quantum mechanics earlier it was the other way around. That means you have to search for Bell states which are violating Bell inequality, and to test that entanglement is a reality.
Yeah.
Okay. Now, is it a Is it a Zidane experiment, or you did the experiment? I mean, you are reporting the real experiment, or it's a thought experiment?
Real experiment.
Real experiment.
Yeah, real experiment.
Yeah. Now, what is the typical intensity of the light you are talking about? I mean, whether we are still in the linear domain, because if you do an experiment in vacuum, then Maxwell equation is a good one. But I mean,
which source are you talking about? So I have to generate entangled photons by using a laser.
Yes.
Okay, so the laser may have a few milliwatts of power, but the entangled photons which are coming out are 1 million to 10 million photon pairs per second. It's a very, very small intensity.
Yes.
So those photons are being used for Bell violation testing of Bell's inequality violations.
Yeah.
They are being sent to the two parties for checking for entanglement. And so, as I was mentioning, the satellite 500 kilometers above the Earth has transmitted entangled photon pairs across thousands of kilometers, one to China and one to Austria, and they have tested that entanglement survives. So these are not thought experiments; these are actual experiments, and these are now routinely conducted everywhere. All those people who work in quantum optics,
Sure. So, I mean, there are lots of inequalities in quantum inequalities one can test in this manner, right?
Yeah, sure.
For example, clauses.
Yes, CHSH inequality. Yes, sure. Yeah. So all these are experimentally done. These are not thought experiments. These are actual real experiments today.
Has it been tested?
Yes, surely.
Okay.
Sir, is it possible to get the PDF of your presentation?
I will send you.
Okay, thank you.
I'll send you, yeah.
Well, if there is no more question, in that case, we thank Professor Tyagarajan, popularly Tyagarajan sir. It was really very exciting and illuminating. He has started from the very scratch of this linear to nonlinear equation, and he has actually traveled through all the latest developments in the field of nonlinear optics. And we are really very proud and again privileged to have him here. I thank all the audience and thank you very much, sir, from my side.
Thank you very much. Thank you for a patient listening. And
thank you. Thank you.
I hope I have shown the excitement in this field and what lies in the future. It's amazing.
Yes, sir.
We are at a good time in this in the development of science and technology, that quantum mechanics is being actually finding commercial applications today. Thank you. Thank you, Mosami, for inviting me. Enjoyed this talk, and I hope the participants also enjoyed the same.
Yes, yes.
Sure.
No problem.
Sure. Thanks a lot.
Thank you very much. Thank you.
Professor
Thank you very much.
Thank you. So, may I disconnect?
Yes, sir.
Yeah, okay.
So
Thank you.
I'll end the session.
Sure. Please. Yeah.
Okay. So thanks a lot to Professor Thiagarajan, sir, for accepting our invitation and delivering such a nice and illuminating talk on nonlinear optics to us. I am extremely happy to have him with us, as personally I feel whatever basic concepts we have learned in the domain of fiber or waveguide optics, that is a major contribution from his work and the books written by him and the legendary person, Professor Arvipato. So I am extremely thankful to him and also to Professor Partharai Choudhury for chairing the session. Okay.
Thank you very much. Thank you.
Thank you very much.
Okay, thank you, sir.
Thank you.
Now we are concluding this technical session 1, and we'll start our next session at 2:45 p.m. And the talk will be by Professor Christopher Fino, and it will start at 3 p.m. Okay.
Thank you.
Okay. Thank you all.
Thank you.
Hello. Professor Hussain.
Yes, yes. Yeah,
Yeah.
please.
Okay. So,
Hello, Professor Dapto. How are you?
Professor, fine. Professor Finot has joined already? Not yet.
Yes, yes, he's there. He's there.
He's there. Okay. Hi. Hello. Hi, Professor. Good afternoon.
Hi.
But probably in France it is not yet good afternoon, no?
It's good morning.
Good morning. Okay, good morning.
Yes, yes. Yeah, please.
Okay.
Hello, Professor Dapto. How are you?
Yeah, fine. What of Finot has joined already? Yeah, he has joined.
Yes, yes, he's there. He's there.
He's there. Okay. Hi. Hello. Hi, Professor. Hi. Hi. Good afternoon.
Hi.
But probably in France it is not yet good afternoon, no?
It's good morning. Yeah.
Good morning.
Yeah.
Yes, yes. Yeah, please.
Okay.
Hello, Professor Dapto. How are you?
Hi. Hi. How are you? Finot has joined already? Yeah. Yes. Yeah.
Moushumidi, we'll start at 3, right?
Yeah.
Uh, repetition was coming. It was in a loop, perhaps. Let us check.
Professor Finot, your place is famous for wines.
Yes. Yes.
Okay. Good quality wines are available.
Yep. Excellent wine.
Yeah. All renowned brands are there.
Yeah.
Professor Finot,
Yes.
your place is famous for wines.
Yes.
Yes. Yes.
Perhaps the best wines in the world, I would say.
Quality wines are available. Yep. Excellent wine.
Yeah.
Yeah. All renowned brands are there.
Yeah.
Yeah. Yes. Reverberation is occurring.
There is a bit of technical glitch. Professor Basu's link is a little bit, creating problem. She's trying to log in again. So we'll be back in 2-3 minutes, I guess. Okay, guess it is solved, right? I hope it's okay now. Moshumidi, no, we can't hear you. Hello.
Ma'am, reconnect from your computer.
Mosumi, you are not audible.
নতুন করেই তো জয়েন করছি তাও তো
Moshumi, you are audible. Will you please start the session?
You are audible now, Professor Basu. You are audible now. It's okay, I guess.
Okay. If I'm audible, then I can start. Okay. Session 2 of our webinar. So in this session, we will listen an interesting presentation in the domain of knowledge.
Now again, your volume is too low now.
I think Professor Hussain, you may start. Better not to wait.
Okay.
Okay.
Okay, so I start. Do you hear me?
Yeah,
Is it okay?
let me introduce you. I am
Okay.
Professor PK Datta from IIT Kharagpur.
Yeah.
Okay, first of all, I really thank Professor Krishnendu Mukherjee, Deepali Banerjee, Said Minhaj Hussain, and Mousumi Basu for organizing a webinar in our field. Really, there was no webinar in our serious webinar in our field. So this is a very good initiative. I thank all of you. But we have got a very renowned professor today in our talk. Okay, Professor Christoph Finot. He's a renowned name in the domain of nonlinear optical pulse reshaping, optical rouge waves, all optical signal processing, allied areas. Presently, he is professor at the Faculty of Sciences and Technology of University of Burgundy, France. He received his PhD from the University of Burgundy in 2005 before spending a year at the Optoelectronics Research Centers, University of Southampton, UK. In 2005, he got the prestigious Marie Curie Fellowship, which is an intra-European fellowship for postdoctoral research and also postdoctoral Lavoisier grant. He is having lots of contribution in teaching physics as well as research. He has been awarded many times for his exceptional contribution since his young age. He was awarded as Best Young Researcher in the General Congress of the SFP and the Belgian Physical Society. At Lille in the year 2005. In 2006, he received the award of Best Scientific Thesis of University of Burgundy, France. He became a member of the Institute of University of France in 2017. He has received the Prime Award for Scientific Excellence, French Ministry of Education in 2009, and also Competitive Bonus Award for Research Supervision, French Ministry of Education in 2013 and 17. He has published more than 440 papers in international journals of repute and co-author of book chapters in the domain of nonlinear fiber optics, published by Springer, CRC Press, etc. He has a strong collaboration with so many internationally renowned personalities like Professor D. Richardson, Professor Petropoulos from the University of Southampton, UK, Professor Sergei Turitsin, Professor S. Boscolo, Aston University, UK, and Professor Wabnitz, University of Brescia, Italy, Professor G. Milot, and many others in the field of nonlinear optical pulse dynamics. It is a great pleasure for us that we will be enriched by his resourceful presentation on the topic of nonlinear pulse shaping in optical fibers, a versatile tool for ultrafast photonics and fundamental wave propagation studies. Professor Finot. Professor, there was a European school on pulse shaping, isn't it? It used to be European Union used to arrange, isn't it? When I was in Italy, it was in I think there
Yeah.
was Capri Island. There was
Yeah.
yeah.
Yeah, you're right. You're
Yeah,
right.
that's very good. Okay. Welcome, Professor. So
Thank you.
sorry, we could not get you physically. We wanted you
Yeah.
physically, but you keep in mind that you have to come to IIEST Shibpur sometime.
Yeah.
Okay, after the pandemic.
Thank you. Thank you.
Welcome, Professor.
So thank you very much for these introductions, and thank you for providing me the opportunity to present my work about nonlinear pulse shaping. So I will share my screen. Here it is.
Please present your screen, sir.
You've got my screen, and I just want.
Yes, it's coming. Yeah.
So today I will try to explain you how we can use optical fibers in order to change the waveform of an optical pulse. And in the previous talk, that was very interesting, it was shown that nonlinearity can be good or bad. Here, we will focus on the good aspect of nonlinearity. So I would like first to acknowledge my colleagues. My colleagues from the lab, Bertrand Kibler, Kemal Amani, Julien Fatome, and Guy Milot, and colleagues from other lab, especially Sonia Boscolo from Aston University and John Dudley from Besançon, that has very strongly contributed to the different results that I will show you today. And I do not forget my student or postdoc, especially Anastasia Sheveleva. I will show results that she has obtained during a master internship. So I will start by a few words about fiber lasers. Fiber lasers, this is a multi-billion market nowadays, and you may have very different durations, starting from a continuous wave, and you can reach pulses with femtosecond durations. And the peak powers that can now be delivered by fiber lasers can be huge. They can exceed the megawatt level. And what is also nice is that you can use several gain processes in a fiber, and you can have access to a wide range of optical wavelengths. And what are the other advantages of fiber lasers? You have an excellent heat dissipation, you have an excellent stability, and it is very efficient also in terms of cost. So many different advantages for this technology. And basically, if you want to have a laser, what do you need? So I will, here today, it will not be a course about fiber lasers, because there are plenty of books when you will be able to find all the bases. Here, if you want to build a fiber laser, you need a fiber. The fiber will provide you the gain you need to have a lasers. And if you want to have a lasers, you also need a cavity that will introduce some losses. So those are here the key ingredients of any lasers. And now, if you want to deal with ultra-short fiber lasers, you will have also to take into account other effects, especially if you deal with pulses that are very short, then you will have to take into account the effect of the dispersion that your fiber introduces. And when your peak power is above several milliwatts, you will have also to take into account the nonlinear effect that may exist in the fiber. There is the Kerr nonlinearity in the fiber. So you see a fiber laser, this is more than just gain and cavity with losses. You have also to take into account dispersion and nonlinearity. And there have been many different architectures that have been developed to balance all those effects. You see, all those lasers, those are fiber lasers with different arrangements of fibers with different properties. My goal here, this is not to describe each of these fiber lasers. Here today, I will just try to show you and to convince you that dispersion and nonlinearity, those they are not drawbacks. They can be really used to make nice things and to change the shape of a pulse waveform. And today I will only focus on cavity-free system. So here I will not describe how the cavity may affect the changes of a pulse when you have really a laser. You don't need really a laser to make nice thing. But first, before giving you some illustration, I would like to describe an optical pulse. And to do this, I will use an analogy with the field of music, with the field of acoustics. And when you listen to a sound, you can hear the intensity profile. So the intensity profile, this is when you have music. So this is when you have a sound, but it does not tell you which sound you have. If you want to know the notes that are in your music, you will have to go in the frequency domain to have a look on the spectrum. And the spectrum will provide you the different notes that are in your music. But the spectrum, it does not provide you when the different sounds are played. So if you want to have a complete picture of your music, what you need, this is in fact the musical score. The musical score, this is a good picture for a sound. And a musical score, this is a time frequency representation. Along the horizontal axis, you have time. Along the vertical axis, you have the frequency. And you see that you may have musical score with the same temporal intensity profile, with the same frequency intensity profile, and the music can be different. So really, it's nice to have this spectrogram, and we have such data in the field of optics. So it's of course a bit more difficult to have access to the spectrogram in optics. So how do we calculate it? Well, it's not so hard to calculate it, because when you have a field, to have the spectrogram, you make the Fourier transform of this field, but not starting from -infinity to +infinity. You make the Fourier transform of the field that is sliced by a temporal gate. That means that you take your field and you just focus on one part of your field, and you just make the Fourier transform of this part of the field that you study. And you will get this kind of spectrogram. Here, this is a spectrogram that is quite typical of a short pulse that goes through a dispersive fiber. And we can record it experimentally. For example, there are devices that are called the X-Frog that are able to provide to a researcher an experimental spectrogram of an ultra-short pulse. So now, how can we change the spectrogram? So there have been huge progress in the field of laser sources. Now you have different wavelength, you have different pulse duration, you have different repetition rate, but the output pulses, most of the time, they are still Gaussian-like pulses or hyperbolic second pulses. And for some application, we would like to generate other shapes. For example, we could be interested to have the optical equivalent of what we have in the electrical domain. In the electrical domain, there are arbitrary waveform generators that can provide pulses with a very high repetition rates, but we are limited by the bandwidth of the electronics. Here, we want to do similar things, but with much shorter pulses and pulses that are optical pulses. So there is a solution that exists and that works very well. This is what is called linear shapings. So what you can do with linear shaping, so you start from a set of frequency, and with linear shaping, you change the spectral phase of your different component. And changing the spectral phase, this is in fact to apply a delay. So you see, from your initial spectrum, you can put the different bits at the place, at the time that you want. And the other things that you can do with linear shaping, this is that you can change the intensity. For example, you can suppress some of the frequency that you have in your signal. So with that, you can already do nice things, but there are things that you cannot do. So now this technique is become quite mature. You see, you have it in a small box. You have the input, so you connect a fiber with your input signal, and at the output you have your signal that has been modified with the delay and the attenuation that you want. It is still quite costly. Here you see the price of this box. This is around 20 kilo euros, so the same price in dollars. There are, however, unfortunately, some limits to these methods. And for example, if you start from the spectrum that you have on the left, you will not be able to make the music on the right. So why is it not possible? There are two problems. The first one, this is that it is quite hard to imprint multiple delay on the same frequency. So it will be very difficult to have here the same bit that is repeated again and again. And there is an even more fundamental limit. This is that in my new music, I have a sound that is not present in my initial spectrum. And here it is not possible with linear shaping to create frequencies in your signal. So you see, there are things that are not possible to be done. And it also leads to another limit. This is that if you want to shape an initial pulse, then you will have to start with a very broad spectrum. So in practice, if you want to have picosecond pulses, optical pulses, you will have to start with femtosecond pulses. So it will require very expensive lasers to reach your target. And another limit, this is that with linear shaping, you can just attenuate the various components. So your process will be, in fact, very lossy. You will really be poor in terms of energy efficiency. And if you think in terms of shaping of a continuous wave, you see that with this process, if you start with a single continuous wave, then you cannot do anything at all with linear shaping. Starting from a continuous wave with a single frequency, you will just have the possibility to generate a continuous wave. So nothing interesting to do with linear shaping on continuous wave. And this is where it is interesting to use the nonlinearity, because with nonlinearity, you will be able to create new frequencies. This is what it has been shown in the previous talk. And in this context, an optical fiber is very interesting because you have a spool of optical fiber for only 1,000 euros. And you will use the nonlinear effect in the optical fiber to generate the frequency that are missing. So I will say a few words about the effect that you may have in an optical fiber and how we can model them. So when you have an ultra-short pulse that propagates in an optical fiber, the first things that you need to take into account, this is dispersion. So dispersions, in terms of modeling, this is the second order derivative of your field, and the level of dispersion is taken into account through a beta 2 coefficient that we have here. Now, if you increase your power, you will also have to take into account the nonlinearity of your fiber. So it will be this additional term in red here, and it will be proportional to the nonlinear coefficient of your fiber. And when we take dispersion and K-nonlinearity into account, we have the nonlinear Schrödinger equation, which is a well-known equation for physicists. Now it is also possible to add other effects. You can include the losses of the fiber or the gain that can be provided in the fiber, and it is quite easily possible to take them into account by just an additional term here that we have. So regarding dispersions, in fiber, what is nice is that we can play with the value of dispersions, and we can have a second order dispersion, so a beta 2 coefficient that can be positive or negative according to the fiber and the wavelength that we use. When we have a beta 2 coefficient that is negative, then we will say that we are in the regime of anomalous dispersions. When beta 2 is positive, we are in the regime of normal dispersions. Now, when your pulse is very short, when you are below the picosecond, it may be useful to add additional terms of dispersions. So you will take into account the third order dispersions, the fourth order of dispersions. There could be also some higher order terms of nonlinearity that may impact the propagations. For example, the Raman and Briand scattering, they may exist in a fiber. And there could be also in some fiber, such as chalcogenide fiber, some terms of nonlinear losses that may affect your propagation of your pulses. And on top of that, well, just before, when you take all those effects into account, you will have the generalized nonlinear Schrödinger equations. So this is the nonlinear Schrödinger equations with additional term, so with several corrections that are included in your model. And typically, this generalized nonlinear Schrödinger equation, this is the equation that is used when you want to model the propagation of a supercontinuum pulse in an optical fiber. And there are other effects that may affect the propagations. Here, the model, the nonlinear Schrödinger equation, this is a scalar model, but there could be also some polarization that may affect the propagation in the fiber. They can be detrimental, but they can also be useful. It depends how you use them. And there is nowadays a lot of research that is currently done regarding the multimode effect that may also happen in a fiber. So for a long time, multimode effect have been considered as a very severe drawback, but it is now possible to handle them and to benefit from those multimode effect. So you see many things that are possible in a fiber. And what is nice, this is that all those effects, you will find them also in nonlinear waveguide. Here, these are a few examples of waveguide that we have used at the University of Burgundy. So those were silicium waveguide or the waveguide made of dioxide titanium materials. And to model the propagation and the nonlinear effect in those waveguide, we always use the nonlinear Schrödinger equations. And for example, we were able to generate a broad supercontinuum in this very small waveguide. You see the square of this waveguide. We have an age of this waveguide that is below 1 microns, and the nonlinear Schrödinger equations with all the additional terms was very efficient to model the very broad supercontinuum that we had. Today, I will just discuss what happened in the model of the nonlinear Schrödinger equation, so I will forget all the additional effect. If you really want to know everything about optical fibers, the Bible of the field, this is the book written by Godwin Agrawal. You will have this great speaker later today, and this is really the reference of the community of optical nonlinear effect in fibers. So now, regarding the consequences of dispersions and the consequences of nonlinearity. If we take dispersion alone, so here I have plotted the spectrogram of a pulse, and let's see how the dispersion will affect the spectrogram. What we see, this is that the dispersion leads to a stretching of your spectrogram according to the temporal axis, so according to the horizontal axis. So you see that with dispersion, you will be able to change your delay of the various frequencies. Now, let's see how nonlinearity taken alone will affect your pulse. You see that when you have nonlinearity alone, so here this is the process of cell-phase modulation, the consequences of cell-phase modulation will be a stretching of your spectrogram according to the vertical axis this time, so according to the axis of frequency. So you see that when you will mix dispersion and nonlinearity, you will have a way to play with your spectrogram according to the to both directions, according to the horizontal and to the vertical directions. So you see here that it is more powerful than the simple linear shaping, where you can just play with the horizontal direction. Here, the nonlinearity, it really had an additional degree of freedom that will be very interesting to shape different pulses. So we'll try to convince you of all this through 3 different examples. So the example that I have selected, this is the generation of parabolic waveform using optical fibers. It will be, I think, the main focus of my talk. I will also try to discuss the generation of ultra short Hall repetition pulses, starting from nothing, from a continuous wave. And in the final example I would like to discuss, this is to show you how we can use optical fiber to describe, to observe very fundamental nonlinear structures. So let's start with the first example, the example of parabolic waveform generations. And here I will show you results of a very simple experiment. So we start with ultra short pulses with a picosecond duration. We amplify those pulses in order to have enough peak power to then generate some nonlinear effect in a spool of fiber. So this is a fiber with normal dispersions. And at the output, we record the temporal intensity profile that we have after the propagation in the fiber. So in this example, and in all the examples that I will show you this morning, well, this afternoon, sorry for you, everything is done at telecommunication wavelength, so with devices that are commercially available devices and devices that are quite typical from the telecommunication industry. So the results. When we observe the temporal intensity profile at the output of the fiber, according to the input power that we have launched in the fiber, what we see, this is that the shape may strongly change according to the level of the input power. And we see that when we are working at low power, we still have a Gaussian pulses. Now, when we increase the power, we are able to generate a parabolic waveform around 500 milliwatts of average power. You can see that the shape that we have after the propagation in the fiber is an inverted parabola. And if we further increase the power, then you will have a flat top waveform, something that is closer from a super Gaussian pulses. So you see here, you just have to tune the average power that you have in your fiber to change the shape of your pulse. Here, you don't need to use any pulse shaper, any linear shaping. You just need a single spool of fiber. Here, there is, however, a small drawback. This is that the parabolic pulse that you generate is not very robust, is not very stable. If you want to further propagate it in another spool of fiber, then it will be destroyed. So there is a way to generate a parabolic pulse that is much more stable. This is to add some gain in your fiber. So if you provide some more energy in your fiber using a laser with a different wavelength, the Raman effect will occur in the fiber. So Raman effect, this is linked to Raman, the Indian Nobel Prize. And the presence of this gain, it will stabilize the parabolic waveform that you generate. And in this context, the parabolic waveform is called a similar-return because this pulse propagates self-similarly. It always keeps the same waveform, a parabolic waveform, and it will be also parabolic in the spectrum. So you see here, we have experimentally generate a waveform that propagates identically whatever your input power is. So there are other things that are nice with this parabolic similar-return. This is that it can be described analytically. There is a solution that exists when you consider very long length of propagation. So this is an asymptotic solution, and you see it corresponds to a parabolic intensity profile. And when you go into the details of the different parameters, what is also interesting to see, this is that regarding the influence of the input pulse property, the parameter that is relevant, this is U0, which is the energy of the input pulse that you use. In other words, you can use any pulse, any input shape, any input peak power, any input temporal durations. At the output, your result will only depend on your pulse energy when you are in the asymptotic solution. So here, that means that the analytical solutions behaves as an attractor of your system. So any pulse that you will send in your fiber will gain will converge towards a parabolic intensity profile. So this is, in terms of fundamental physics, it's very interesting. And we have tested experimentally. We have used pulses with different input pulse durations. And at the output, we always have the same properties in terms of spectral width, in terms of peak power. And here, this is another illustration of this attraction process. You see that we can change the input pulse duration by 1 order of magnitude. You will always converge towards the same temporal duration at the output. So here, this is the asymptotic solution. This is the ideal case. This is the nicest case. Now, in practice, you are not in the asymptotic regime. So you cannot use the analytical solution. You still have to use the nonlinear Schrödinger solution. And if you want to explore all the various possibilities that may exist, there are several parameters that you may change. For example, you may change the value of the second order dispersions. You may want to change the value of the nonlinear coefficients. You may want to change the value of the gain or the loss, or you may want to change the fiber length. And you can also play with the initial peak power, the initial temporal width. So you see, in terms of the number of degree of freedom, there is at least 6 degree of freedom that you can explore. So this is a space of parameter that is quite large, even if your equation is very simple. So you can gain a lot of time if you use normalized unit and scaling, because your nonlinear Schrödinger equation, you can use normalized variable. So you may start by using a normalized time that will provide you what is usually called a dispersive length. So this is a typical length over which the dispersive effect change your pulse waveform. And it will also lead you to a normalized gain of attenuation, as well as a normalized distance of propagation. The other normalizations that you can do, this is to normalize your field according to your input peak power. And in this case, it will lead you to a nonlinear length that is typical and the length over which the surface modulation will distort your spectrum. And combining the nonlinear length and the dispersive length, you will have the soliton number, which is the ratio between the dispersive length and the nonlinear length. And when you combine everything, you have a new version of the nonlinear Schrödinger equations with written in terms of normalized unit. And in this case, what is nice, this is that the space that you have to investigate is now reduced to only 3 parameters. So it will be the parameter delta, it will be the normalized distance, and the soliton number. So here you have been able to reduce the complexity of your system. And that means that your conclusions, when you have conclusions with a given set of parameters, you will be able to apply them to very different fibers. You will just have to use the normalization the other way. So your conclusion, you will be able to apply them to telecommunication fiber, to cacogenal fiber, or to integrated waveguides. But if you want now to explore really in a systematic way this complete space of parameters, it will require quite a lot of simulations. If you only take 40 value of each parameter, which is not so large, then it will lead you to 64,000 simulations. And even if you use a very efficient algorithm, such as the split-step Fourier, then you may need more than 1 day and a half to cover all the space. So we have worked to try to have some way to speed up things. And one thing that we have tried to explore that is quite trendy, this is to use artificial networks. So artificial networks, this is to try to mimic what we have in the brain. And how can we mimic it quite simply? Well, you consider that you have different input data. So this is here x1, x2, x3, xn. So this is your parameters. Then on each input, you will put a weight, W1, W2, W3, up to Wn. And you will make the summation of all the weighted inputs. So for the moment here, it's just some linear mathematics. So it can be very easily be done with Octave, for example, with MATLAB. And once you have made these summations, so in this summation, you may also have to put some level of bias. Then you use an activation function, such as a sigmoid, for example, and you will get the output of your artificial neuron. So you see, between the input and the output that you have, everything is ruled by a set of weight and a bias. So there are different coefficients that you will need to give to the neuron to work efficiently. So in practice, what we do not consider a single neuron. We consider tens of neurons, and we put those neurons on different layers. So typically 3 layers here. And in this example, my input parameters will be the Soliton number, the propagation distance in normalized unit, and my level of gain attenuation also in normalized unit. So those are my input parameters. And at the output, what I want to obtain, this is the temporal intensity profile and the spectral intensity profile. And here, the main difficulty, it will be to find all the coefficients of the various neurons. For example, if I have 30 neurons that are involved, for each neuron, I will have to find all those coefficients. So how does it work in practice? Here, what we do, this is a supervised machine learning. That means that the initial stage, the starting stage, it will be to collect data, to create a data set that needs to be quite large. Typically, we use 10,000 simulation based on the nonlinear Schrödinger equation to create this data set. So this data set, it is made of the input parameters and the corresponding output parameters that we obtained with the nonlinear Schrödinger equations. So here we need some time to collect all those data. Then there is a very fast stage where we will normalize everything just to have our code running fast. And the main part, this is the training stage. And this training stage, this is to find the best combinations of the various coefficients of the neuron. So the best coefficient for the weight and the bias. And here, usually this is done using black box. So there are algorithms that are already available. You can find them that are already written in MATLAB, in Octave, or in Python, and they will work for you. They will give you all the parameters that will be used then for your neural networks. So here, you don't need to work so hard to find those parameters. It will be done for you with very efficient algorithms. And when you have found a set of parameters that seems to work quite well, you have to validate them. So you never use your full set of data to make the training. You always keep, let's say, 20% of your data to make a validation on a data set that is not known by the training algorithm. And if the training was efficient, then you are able to validate your neural networks. You know that it works very well and that it can predict accurately for a known set of input what you have at the output. And when you are sure of it, you can use it. And this is what we have done. And what is nice with neural network that I have not said before, this is that they are extremely fast. Once you have your neural network that is trained, then it will be able to really make things very, very fast. And you will be able to process hundreds of thousands of simulations in only a few minutes. So the neural networks, it does not give you any new insight in terms of physics. What it provides you is just speed. But there are other things that can be interesting. This is that you can do the opposite with the neural network. So you can train new neural networks starting from an intensity and a spectral intensity profile to retrieve the propagations parameters. And this kind of things, this is not possible to do it using the nonlinear Schrödinger equations. And here, the neural networks will provide you your propagation parameters. And it is extremely accurate to do it when it is properly trained we have here errors on the solitary numbers and the propagation length and on the level of gain of attenuation that is extremely low. So here, this is really a new tool to identify the propagation parameters when you have a given intensity profile and spectral waveform. So I will stop here with neural networks. With neural networks, I have just discussed is what we call feed-forward neural networks. There are many other neural networks that may exist, and if you are interested in this subject, there is a review article that has been published with Gary Gunty, with John Dudley, with Sergei Turistin, where they describe how these neural networks can be used in ultrafast photonics. So this is really an up-to-date review. So I really recommend this review if you are interested in this field. So now I'm back to the problem of generating parabolic pulse using the nonlinear Schrödinger equation with gain. We have seen that it was very efficient, but sometimes we do not want to have gain. And in that case, there is another possibility where you do not need to provide another pump in your system. This is to use a fiber where you change the parameters of propagation according to the distance of propagations. So it can be shown that mathematically, it is possible to replace the nonlinear Schrödinger equation with a term of gain by a nonlinear Schrödinger equation without any gain, but with a dispersion that change according to the propagation length. And it works also very well. We have validated in Dijon. You see here on this example, we start from an hyperbolic second pulse, and after propagation, we have a parabolic waveform with a chirp that is highly linear. And here I just would like to show another example made by Professor Bazou in your university, where we have where they have numerically investigated the possibility to replace a dispersion decreasing fiber, by a set of segments with fixed dispersions. And they also observed in their numerical simulations that the input pulse reshaped into a nice parabolic waveform. There are, with this parabolic pulses, many things that you can do in terms of regenerations for optical telecommunications to generate ultra-short high peak power pulses. And I would just want to show you a last application that is a bit strange. Here I have taken the parabolic pulses and I have inverted its spectrum, its chirp. And what we can see, this is that when I increase the power, here's just as experimental spectra that I have taken when I increase the power. And you see that when I increase the power, very surprisingly, it leads to a compression of the spectrum. And this is quite unusual because usually we associate the self-phase modulation, so the nonlinearity in the fiber, with expansion of the spectrum. But when you know how to undo nonlinearity, you can do the opposite. You can use nonlinearity to focus your energy on a very narrow bandwidth in your spectrum. So you see, nonlinearity, it really opens a large set of possibilities. So those parabolic pulses, they are a building block of fiber lasers. So there have been very different laser architectures that have been built over those parabolic pulses. And as you see, this is still a subject of very intense research. We still see lasers, fiber lasers, where studies are made on those parabolic pulses. So there are other waveforms that can be generated by using this nonlinear shaping in a fiber. For example, you just have to put an additional segment of fiber. Here, a length of 250 meters in a single mode fiber. And at the output, what you obtain, this is a triangular waveform. And you can also make other things with it. If you had another spool of fiber, so here this is a fiber that was 1 kilometer long, and at the output, you maintain your parabolic, your triangular waveform, but you have splitted your spectrum into two well-separated peaks. So you can see that playing with different pieces of fiber, you can really do very interesting things. So on this example of triangular pulse generations, I will once again want to show another example that is this once again done in your university by Professor Basu that is used step index chalcogenide fiber. So a fiber that is very different from the one I used previously, but the nature of the fiber is not so important because the governing equation is the same. This is a nonlinear Schrödinger equation. So I have finished with this first example. I will go quicker on the other two examples. The other example I would like to show you, this is how it is possible to generate ultra-short pulses starting from a continuous wave. So the goal this is to start from something that is perfectly continuous, so with a single frequency, and to end with ultra-short pulses. If you have ultra-short pulses, that means that you have a wide range of frequency that are in your signal. And here is the experimental setup that we have developed. It was last year in Dijon with my student Anastasia Shevaleva. And you see that the setup, there are not tens and tens of optical components. There are only a few. You have a continuous wave lasers. You have a device that is a phase modulator. So I will explain you why we use this device. And this device is linked to an electronic clock that will deliver the initial signal that we will use as a clock. Then we will make some linear shaping and the signal that we have generate. We will amplify it with an absorb fiber amplifier to generate nonlinearity in a highly nonlinear fiber. And after this highly nonlinear fiber, we imprint some dispersive effect, and it can be done through a dispersive fiber with the length that has been well chosen. So let me now explain you why it is interesting to use this cascade of elements. So we start from a continuous wave. So nothing very interesting at this stage. Then we modulate the phase of this continuous wave. And you have to know that when we change the temporal phase, if you take the derivative of the phase, it gives the instantaneous frequency. So if we imprint a phase modulation over time, it will change the instantaneous frequency. So after the phase modulator, you will have a sinusoidal change of your frequency. So the phase modulator here, it has led to the generation of some bit notes in your music. So now you will be able to make interesting things. The next step, this is to use linear shaping. And this linear shaping, it will enable us to have the frequencies at the right time. We can replace this stage by a spool of fiber. It could be possible. It would work, but it will be slightly less efficient in terms of performance. So what we have after the first stage, you see it will be now pulses. But they will not be short enough. And if we want to get them shorter, we need to increase the spectral content, and we will do it through the propagation in the highly nonlinear fiber. It will help us to generate new frequencies. And in the final stage, we put all the frequencies at the same time by the final piece of dispersive propagations. And I've got here my ultra short pulses. So this is the concept. How does it work experimentally? You see that after the first stage, I've already have some some short pulses. You see the time scale here. We have a duration that is below 10 picoseconds. This is a duration that is not possible using standard electronics. And you see that the spectrum is already different from a single frequency. After the fourth stage, so after the propagation, the highly nonlinear fiber, I still have a pulse with a similar duration. It's slightly reshaped. It is something that is more parabolic. But the biggest change, this is in the context of the spectrum. You see that I have a huge broadening of the spectrum that is now more than 1 terahertz of spectral wave. And after the final stage, you see that I am obtained very nice ultra-short pulses. Here we have measured the temporal duration, and it was below the picosecond. It was 900 femtosecond. And we are able, with this simple device, to reach repetition rate that are above 100 gigahertz. And what can be also noticed, this is that if I compare the black curved with the dashed red lines, we have a nearly perfect agreement. And the dashed red line, these are the result of the nonlinear Schrödinger equation. So you see that this equation is very robust to predict what we have at the output of our optical setup. We can really here predict quantitatively what will be the output. And when we make these numerical simulations, we do not adjust any parameters. So I will now go through the last set of examples that deals with the generations of very fundamental nonlinear structures in optical fibers. And I will start once again from the nonlinear Schrödinger equations. And it's quite inspiring to compare this version of the equations with the equation that rules the propagation of water wave in oceans. And you see that the equation is nearly identical. You just have to switch the longitudinal and the temporal coordinates, and you have the same equations. That means that light, when it propagates in a fiber with anomalous dispersions, it will be changed in the same way than a wave that propagates in an ocean. And what about normal dispersions? In normal dispersions, it is interesting to turn the nonlinear Schrödinger equation into a set of two equations, two coupled equations, and those equations are known as Saint-Venant equations, and they represent the propagation of light in shallow waters. So you see, according to the regime of dispersion that you will use, you will be able to explore what happens in oceans and what happens in shallow waters. So in fiber, you will be able to observe undulables, or you will be able, for example, to observe rock waves that may exist in the oceans. And we have tried to do both in Dijon. For example, we have observed undulables in normally dispersive fibers, and we have observed rock waves, and I will give a few additional words about those rock waves. Those rock waves they appear from nowhere and disappears without leaving a trace. This is why they have been very hard to study in oceans. They were never really been seen experimentally, and in our case, we have focused on a mathematical solution that was proposed by Howell Peregrine in 1983. And this solution has never been validated experimentally. You see, this is a rational solution, and we have tried to validate it in the field of fiber. And once again, the principle of our technique is quite simple. We start from a continuous lasers. We put a small modulation on the top of this continuous wave. We amplified the resulting signal to get enough nonlinearity, and we propagated in a simple single mode fiber, the most standard one, the one that is used for optical telecommunication. And at the output, we detect the results. And when we do this, we can see that the initial small modulation gets compressed, and instead of the small modulation, what we see, this is some very powerful spike of light that are generated. So we have been able really to validate the emergence of the prediction of the wave predicted by Peregrine. And if we compare the results of the experiment with the results of the nonlinear Schrödinger equation, we see that we have a very nice agreement. And sorry. And you see here how the small modulation is very strongly reshaped. And what you can see, this is that when we compare the analytical prediction of Peregrine, it perfectly fits our experiment. So we are really be able to demonstrate a new nonlinear structures in optical fibers. And this new nonlinear structures, it has then helped to understand what happens when you have, for example, wave turbulence, when you have a compression of very powerful pulses, or when you have modulation instability. So it has opened a new way to see the nonlinear dynamics that may exist in fibers. And then it has been also demonstrated in other fields, such as hydrodynamics by Amin Chapshub and Neil Akhmediev, that has also done a lot of works in fiber optics, as well as in plasma, for example, with works made in India by Beilong. And it is not so surprising because all those fields, they have in common the nonlinear Schrödinger equations. This is really the same equation that governs all those fields. And this is not the end of the story, because there are plenty of other nonlinear solutions that may exist and that we have explored in fibers, such as the Akhmediev brothers, such as Kuznetsov-Mas solitons. And you see that all those different coherent structures, they can then interact, they can collide. So there are plenty of things that could be explored. There are really a lot of many different studies that can be done, both experimentally and theoretically. So this is now time for me, I think, to conclude. I have tried to show you that nonlinearity, this is not always the bad. It can be, on the contrary, very good. I think that the previous talk have already convinced you of this. You can use nonlinearity in high power laser, in ultra-fast processing, in telecommunications, and there are plenty of degree of freedom that can be used. Here I have not spoken about polarization. I have not tell anything about multimode. These are other degree that are still quite unexplored. And what is nice, this is also that if you want to do fundamental physics, you can use also fiber optics. Fiber optics, this is not restricted to the field of optical from telecommunication. You can use them as an ideal testbed, for example, to study new nonlinear waves. And if you are interested in the field of laser, of course, there is plenty of things that can be done with ultrafast fiber lasers. So if you're interested in the subject, you can find other few things in this book that I have co-authored with Sonia Boscolo. And I would like, once again, thanks the organizing committee for this invitation. I am very happy to give this talk, and I would like to thank all my colleagues that have taken part in those different studies. So thank you very much.
Okay. Thanks a lot. Thank you, Professor. So there are some questions. So should I read these questions just one by one? Okay, let us thank first. Okay. So, okay, I see Professor Binoy Krishna Ghosh, he has a question on how to calculate the cardinal
He's not
linearity.
professor. He's our student, PhD
Okay, your
student.
student. Okay, PhD student. Okay.
Okay.
How to calculate the cardinal linearity of different waveguides such as reach, slot, etc. Especially how to calculate the effective area of nonlinearity calculation for those waveguides.
Okay, for this, you will need to do some computation. So you will need to find the modes of your waveguides, because every time here we deal with guided propagations. So you need to identify your optical modes that are able to propagate in your fiber, and this mode, it will depend on the design of the fiber. And according to the mode that you will find, you will have different dispersion, you will have different effective area, because the nonlinear coefficient, this is the result of the nonlinear coefficient, so the coefficient of the material, and this is also the result of the effective area of your mode. So when you have a mode that is very strongly confined, you will have a very high nonlinear coefficient. So to identify your mode, in the simplest case, you can do it analytically, but usually it's easier to use numerical simulations. You can find various programs that are able to solve it, or you can use also some other software that now can enable you to do it. So with finite elements that are based on finite element modeling.
The same student has another question, that how can you use NLSE in a fiber of diameter, sub-wavelength diameter, if the diameter of the fiber is much smaller than the wavelength?
Well, yes. In this case, when you have very small diameter, there can be a few tricky things that may happen, because the assumption that are usually made when you have a fiber can become not valid anymore. For example, usually we only consider the propagations of the electrical field, and when you try to investigate sub-wavelength components, then you may have also to consider the magnetic field, and in that case, the vectorial property of light, you have to be a bit cautious about them. So, well, in principle, the NLSA could work, but perhaps the initial assumptions are not valid anymore. So for this, there have been a few works that have discussed the validity of the nonlinear Schrödinger equations in the case of fiber with really very short cores. Sometimes you have to be cautious. You have to be cautious.
Actually, sir,
because
that's my question. Whenever we are going to solve sub-wavelength diameter fiber, in that case, we have to solve the vector wave solution. That's fine. But using vector wave solution, though I can calculate the GBD parameter or nonlinearity parameter, but whenever I am going to introduce in NLSE, then most of its part is going outside as evanescent field. So I cannot take that part in our calculation. So that's the reason how can I solve. Because whenever I am solving to if I want to see the pulse propagation for very short length of the fiber, minimum 10 centimeter or so, then also I have to use NLSE or so. So that's why I am asking how I can use NLSE in this case.
well, after there exist some other version of the NLSE. The NLSE, you can also use it in using in the spectral domain. So because here what I have shown, this is the version written in terms of temporal units. But if you move in the spectral domain, then it will be the frequency that will appear in your equations. And sometimes it's easier to make the link with some of the property that you have obtained from your simulation software. You will be able to include additional terms directly in the frequency domain. It should be easier in that case. But the model of the NLSE should remain valid. Then perhaps you may have some problem of stability when you make the numerical simulations, because if your spectrum broadens too much, then you may become quite unstable, and you have in that case to be very careful about the numerical aspect of the solving of an LSE.
And next question from Binoy is when you increase the when you try to make a flat top pulse by increasing the power, input power, you can, there is a instability. To stabilize it, you use a Raman pump. Okay, Raman pump. Okay, so so is it that your Raman is giving some gain, or what is just like a negative feedback to stabilize it, or what type of stabilization is it?
So here the effect of the additional laser that I involve, I will try to put the slide again.
Yeah.
Yes. Okay. So in fact, I use it. I call it Raman pump. I should perhaps it will be easier to say that this is another laser that will provide some gain into the fiber. So here I have chosen the wavelength of the laser to be shifted by 100 nanometer compared to the signal that I study. And when in silica I am shifted by 100 nanometers, I have a strong Raman gain in that case. So I will have a transfer of energy from my laser to the signal. So it will lead to amplification. And here, what is nice with the Raman process, compared to the other gain process that are usually used in optical fiber, such as the Erbium dot fiber amplifier, this is that I can use the Raman effect in any fiber. I do not need to have Erbium ions that are in the fiber. So I do not need a specific fiber. And with this, I can use a fiber that is 6 kilometers long. I just need here to use this additional fiber with the wavelength that have been well selected to be, in that case, I think it's 1455 for the laser I used.
So in this case, I think Ginzburg-Landau equation you have to use, isn't it? Instead of NLSE, with gain you have to use Ginzburg-Landau equation.
No, here I do not with gain. Well, for me this is not the Ginzburg-Landau, because for me Ginzburg-Landau, these are there are also additional terms that I have not put here. For me in Ginzburg-Landau there are also some limitations of the bandwidth, and here I do not have any bandwidth limitations. So the level of complexity of Ginzburg-Landau is one step higher again.
Yeah.
And we use Ginzburg-Landau, for example, in lasers, because in that case, we have the cavity effect that will limit the spectral wave. So it is
I have a
useful,
question.
but for more complex phenomena.
Okay, Professor Sarkar has a question.
Professor, very nice lecture. You have chosen a fiber which has got a geometrical shape. Now, if we choose some bow type fiber or elliptical core fiber or photonic crystal fiber with various air holes, so what will be the effect of those shapes on your pulse? Or can you expect something if I fill the air holes with some liquid like that?
When you begin to deal with polarization, you can see many different things. It is extremely interesting. And here it's quite hard to give a simple answer because what will happen when you will have birefringence that will appear, this is that you may have cross-phase modulation between the pulses that will propagate according to the two axes of propagations. And the cross-phase modulation, that means that what will happen on one polarization will also affect what happens on the other polarizations. And it may really lead to very different things. If this birefringence is very small, you may observe some coupling between the two structures. There have been some papers that have shown it. And if the birefringence is very large compared to the overall propagation of light, then the pulse will get in the temporal domain separated because the delay between the two axes of propagation will be bigger than the temporal duration, so they will not interact anymore. And in that case, both pulses may evolve towards a parabolic shape independently from the other axis.
But so, in case of photonic crystal fiber, you can increase the modal range. It can be endlessly single moded. So what will be that effect if you use photonic crystal fiber in just to shape your pulse?
Yes. Well, if you are endlessly single mode.
Single mode photonic crystal fiber. So you are having, if small d and capital lambda is d by lambda is less than 0.44, you can have endlessly single moded. So you may have better prospect.
Yeah. But single mode, that means that you have a single mode, but you may have two polarization most of the time in photonic crystal fiber, because with the symmetry of your photonic crystal fiber, you have two polarization mode that may exist with a slight difference in terms of index of propagations. And in that case, you will still have a delay between the two pulses, and you may still have a coupling between the two that may exist. So usually, in that case, it's better to use a vectorial model, or experimentally, if you are really sure that you can put all the energy on one axis, in that case, you may still use the scalar model of the NLSR, and it should work in that case. But it really needs you to be sure that you are on the axis of your fiber.
Okay, thank you. Is there any study on photonic crystal fiber involving pulse shape? If it is circular core, then there will be no polarization as such effect. But is there any study of this parabolic pulse shaping involving photonic crystal fiber?
I do not remember of such studies. Most of the studies with photonic crystal fibers have been done to generate supercontinuum pulses. And usually what will also come into play, this is the third order dispersion. Here I have neglected this third order dispersions, and in the end, the third order dispersion may break the parabolic pulse. In that case, there is what we call a wave breaking effect that appears on one side of the pulse. And regarding the influence of this third order dispersion coefficient, there are a few studies that exist. Those are the study of Sonia Boscolo, for example.
Yeah,
And
thank
Sergei
you.
Chikrin.
Okay, I have,
Thank
okay,
you.
I think no more questions. So I have just one small question. That peregrine wave that you mentioned,
Yeah.
does it satisfy nonlinear Schrodinger equation? How did he reach, how did he get this peregrine wave?
So it's here. This it satisfies the nonlinear Schrodinger equation. So
Okay.
if you take the peregrine solution and if you put it in the nonlinear Schrodinger, you will see
Okay.
that it works. So
Okay.
this is something that is different from the solitons, because the solitons, this is a stationary solution. It keeps the same shape unaffected. But yes, this is really a solution, and there is no approximation. There is no term that is forgotten. This is an exact solution, and this is one among several other one. The other ones, those are the Akhmediev brothers, the Kuznetsov-Ma solitons. They are also exact solutions, and the fundamental difference compared to the soliton solution, that is usually the best known solution of the nonlinear Schrodinger equations, this is that those solutions, they lie over a finite background. So for the usual soliton, the wings, they go down to 0.
Yeah.
But in the case of all those solutions, and we see it on the experiment, you see we have a background. We always have a kind of continuous background. And this is really specific of those solutions. And I think the presence of those background, this is why at the beginning people have not tried to study them. They were more interested by the solitons, because the solitons, there is not this background, and they can be directly useful for optical telecommunication, for example.
Another thing, that pulse shaping inside the cavity, how is it possible? Say, when you have a fiber laser, so in the cavity itself, say all normal dispersion fiber laser, these are some sort of pulse shaping is there inside. Okay.
Yes.
So can you suggest, say, many things like pulse splitting, or when you go for higher order mode locking, can you set the pulses inside the cavity?
Yeah. Yes, we
that
can.
may be very interesting. Then you can get directly from laser the shaped pulse.
Yes, it is possible. So, for example, on this example, well, this is a recent work. I will just try to make the setup bigger.
Yeah.
So this is a cavity studied by my colleague John Dudley. So this is a recent work in Scientific Report. And what we see, this is that there are different segments of fiber. And in each segment, there is a kind of reshaping. And the condition when you have a cavity, this is that after a turn in your cavity, you have to be similar to what you had a turn before. So you have to be identical. You have a full cycle. And typically, if I take a point, so if I take the point A, I have in this cavity a segment of fiber with an Abiob dot fiber amplifier. And so in this piece of fiber at point B, I will have parabolic pulses. And this is what we observed on the two figures I have plotted below. There is the spectrum that is parabolic-like. There are small fluctuations. And the temporal intensity profile is also parabolic. Well, we do not see it clearly on the result because it is plotted on the logarithmic scale. But believe me, we have a nice parabolic shape. So after the coupler at point D, with this laser, it is possible to obtain directly parabolic pulses after these lasers. But
And
then
what is the fluctuation level, or maybe I should call noise level, in terms of say jitter noise and as well as maybe amplitude fluctuations?
here it's quite nice. It's quite
Okay.
good because, well, let me just finish the loop.
Say if you have a all normal dispersion fiber laser,
Yeah.
that one is the best in terms of say jitter noise or amplitude fluctuations. Self similarity on how does it stand as compared to this one, all normal dispersion?
What I cannot give you numbers. What I can tell you is that this kind of architecture is very stable because this is the kind of architecture that is explored by the people from NIST, for example.
Yeah.
So they use this kind of architecture. They do not use, for example, the architecture that relies on solitons, because you can have a fiber lasers where you only have components with anomalous dispersions. And in that case, it's not so stable. In the field of with normally dispersive fiber, it's more stable because there are attraction process. In fact, in this cavity, there are two attraction processes that acts. The first one, it is in the normal part with the absorbed fiber. And there is a second one because there is a small part with a single mode fiber. And in this fiber, it has been designed so that there will be a soliton, a usual solitons. And the soliton, this is the other attractor that you may find in fiber. So you have a combination of two attractors that make the laser quite stable. And you have also in this cavity a filter. So the filter, this is to limit the spectral bandwidth, because in VDFI you always have spectral broadening. So if you want really to have a stationary solution, you have to limit your spectral extent. And when you put everything, you have something that is stable over a given range, because if you change too much the power of your diodes, then what you will generate at the output, it will not be a single pulse per turn, it will be a doublet of pulse. So, and then it can become chaotic. So there are a lot of regimes that can be seen. When it runs in the single pulse regime, it is supposed to be quite stable. But if you further increase your power, then you will lose this stability. And in this article, there are the different regimes that are shown using new measurement techniques such as the dispersive Fourier transform, which is very interesting to catch the spectral features turn after turn. And perhaps Professor Agraval have seen the subject of this talk. Perhaps he will say a few words about the DFT, the dispersive Fourier transform, that is directly linked to the analogy between the spatial and temporal propagation in fibers. But it's very exciting, this subject of fiber lasers, because there are many things that can be discussed. It can be really very complex, but this is the interest of the setup.
Yeah. Okay. Thank you, Professor. Thank you, Professor Fintop. I think we have no more questions. So, Professor Basu, you may
Yes.
now take in. Okay.
Yes. Thanks a lot to Professor Fino for accepting my invitation and delivering such a beautiful and attractive lecture to us. I personally feel that the people who are working in this domain or who are getting interested has been benefited a lot by this talk. And I feel so happy, as you have also mentioned our group work in this prestigious talk. I'm also extremely thankful to Professor Prashanto Datto for chairing the session. And due to some technical glitch, I could not start the session in time and missed some part of the talk also. So let me introduce Professor Datto once. Professor Prashanto Kumar Datto is from Department of Physics, IIT Indian Institute of Technology, Kharagpur. He is currently head of the Department of Physics there, and he joined this institute in 2000 and had been working on lasers and nonlinear optics for a long time. Recently, he developed a femtosecond laser laboratory for study of ultrafast science with facilities like palm probe spectroscopy, time-resolved MOKE, terahertz spectroscopy, and JET scan. And he has more than 100 publications in internationally referred journals and has produced 12 PhDs so far. And finally, thanks a lot to both of you for presenting this very nice technical session. Okay, so finally, I have a request. The PhD students have a request to take a photograph. If you all please put your video on, they will take a screenshot picture. So if you all please put your video on, it will be nice.
Okay.
Just a minute. Okay. So we are extremely happy that I had this session with all of you.
Thank you.
Professor Pino, thank you a lot.
Thank you. Thank
We
you,
are
Professor.
working in the same field. So I'm
Please,
Thank you
extremely
very
happy.
much.
please visit sometime in India.
Uh, if you have any plan in future, please visit to our institute.
Okay, yes,
Thank you.
Okay.
Thank
for
you.
sure.
Thank you.
Okay.
Thank you. Thank
So,
you very
Mosumi,
much.
when will be next session? 8:30.
The next session will be at 8:30. Professor G.P. Agoral will be the speaker. The next session will start at 8:30. 8:30 p.m. Indian Standard Time. Okay.
So, I will
Thank
enter
you.
8:20.
8:20 it will start. Okay.
Okay.
Thanks a lot.
Thank you.
Okay then. Okay.
Okay.
Bye. Okay.
Okay
Bye.
then.
Okay. Bye.
Okay. Bye.
Okay,
Thank
bye.
you. Thank you.
Thanks a lot.
Goodbye.
Bye. Goodbye.
Moushumi, Dr. Chumki Shah has joined.
Yes, I have seen.
Unmute karo.
Am I audible?
Yes,
আমার
yes,
কথা
yes. You
শোনা
are audible.
যাচ্ছে?
হ্যাঁ, শোনা যাচ্ছে. It's fine. It's okay. It's okay.
আচ্ছা। চুমকি? হ্যালো চুমকি?
হ্যালো মৌসুমী।
হ্যাঁ।
হ্যাঁ।
ভালো তো?
হ্যাঁ,
ভালো
ভালো
আছিস?
আছি। হ্যাঁ, ভালো আছি। ঠিক আছে, এখানে আমি দেখাচ্ছি, আমি এরকম করে রাখছি।
মৌসুমী, hello
Yes.
মৌসুমী,
হ্যাঁ।
প্রফেসর আগরওয়াল জয়েন করেছেন কি? Has he
No.
joined?
No.
একটা কি মেল বা কিছু করবে ওনাকে? 8 মিনিট
করছি তাহলে।
বাকি আছে। প্রফেসর সরকার?
প্রফেসর সরকারও করেনি মেল। দুজন প্রফেসরকে ফোন করছি, কিন্তু ওনাকে একটা মেল করি, ওনার ফোন নাম্বার তো আমার কাছে নেই, প্রফেসর আগরওয়ালে।
ওনাকে একটা মেল করো ইমিডিয়েটলি। Left the meeting. You left the meeting, বলছে।
কে left the meeting?
না 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 ঠিক আছে।
উনি কি ঢুকেছিলেন?
না 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 উনি ঢোকেন। উনি ঢোকেন নি, উনি ঢোকেন।
Hello, Krishnendu. Can you hear me, Krishnendu?
Yes, I can hear you. বলো সুকেন্দা।
You and Mosumi said some Professor Sarkar. Am I or somebody else?
আমি বুঝতে পারলাম না কি বলছো।
No.
Sarah has joined.
Welcome, Professor Agarwal.
No,
No, that is Somnath Sarkar, Professor Somnath Sarkar.
Okay, right, okay. I was afraid.
No. Welcome, Professor Agarwal.
Hello, Professor Agarwal. How are you?
Professor Agarwal, unmute yourself, please. Professor Agarwal, your microphone is mute now.
Can you hear me now? Hello?
Yes, sir.
Yes, I can hear you.
And then you can see my image, you can see me also, right?
Yes.
Okay,
Perfect.
okay. So you have to tell me how to turn on I want to display. I mean, when I have to display, you have to tell me how to turn it on. I can present now. I see something called present now.
So you have to go to present now, and from there. And you have to go to present now, and then it will take the permission, and you can share your screen.
Okay, all right. Okay, so I will do that when time comes. Yeah, okay.
Okay. So I am starting the formal procedure after that. Okay, just I will call the session chair, and he will.
Okay, that sounds good.
Okay.
Yeah.
Okay. So let me start.
Yeah, sure.
Okay.
Now we may wait for 5 minutes. The time is 8:30, so it's 8:25.
Okay.
We still have 2 minutes.
Yes. We may.
Participants too.
Okay. 5 minutes. Only 5 minutes.
You have some informal talk now.
Okay.
But it's better to wait for 5 more minutes.
Professor Agarwal, how are you?
I'm doing well. I'm fine. I mean, this is a strange time because of this COVID virus, but I've got my 2 shots, so I'm doing fine. I'm doing better. But I've been teaching from home for last 1 year. I've not gone to my office. I'm doing most of the work from home. But I think it's starting maybe in a month or 2 months, we might be able to go back. I think that I'm hearing that it's getting better here.
But you visited our Department of Electronic Science. At that time, Professor Mousumi also came. You gave lecture in Science College.
Right. And that was a long time ago. That was 10 or 12
time
years
ago, in 2008.
A long time ago. Yes, I remember that. Yeah, right.
You sat on my chair.
Yeah.
After that, we met in CGCRI once.
CGCRI, and then we visited.
Right.
We heard also your lectures there.
Yeah. So let me ask you, how many people are present or attending this webinar, this symposium?
Actually,
in general,
almost 100 people, or registered people is almost 170 like that, 170 or 180 like that. So they are attending the lectures almost 100.
Okay, good. So that's very nice. Very nice to hear that.
Professor Fino has also joined.
Yeah, I just noticed that. Hello, Christopher.
Hello.
Hello, good to see you.
Yes.
Professor Sarkar.
So should I start or just?
Hello.
3 minutes.
Hello.
Professor Sarkar, can you please put your camera a little bit downward? Your face is not fully visible, so it's better if you kindly.
Is it better now?
Yeah, it's
Now
fine.
it's okay. Now it's fine.
Okay.
It's okay, sir.
Okay. All
Yes,
right.
it's perfect now.
Okay. So let me maybe show my slide to see whether it's working or not. So I'm going to click on the present now.
Yes. That you can
Okay,
check now.
present now and your entire screen. Okay, I can do that. Entire
Yes,
screen.
then select that.
And share. Let's see this. Share. It's not going yet. Okay, here it comes. Share.
So
And
you have to
now I'm
select.
going.
You have to select the whole screen. Click on the screen, sir. Yes.
Yeah. So can you see
It's
my
working.
slide?
Yes.
Yes, sir.
Okay. Good. So that's very nice. Good. So I will stop sharing for the time being, I guess.
Okay.
Yeah, we'll come back to this afterwards. But it's very slow.
We have around 50 more than 50 participants.
Right.
In the Google Meet platform. Other than this, we are actually streaming this meeting through YouTube. So that is open to everyone. We are having the live streaming. So the participants outside this Google Meet, they are connected live.
পরে বলছি শুরু হয়ে গেছে
Okay. All right.
চলো মৌসুমী শুরু করো তাহলে।
Yes, it's 8:29 now. So Maushumi, you can start.
Okay. So good evening, everybody. Welcome to all for this technical session 3 of the international webinar. All of us are feeling extremely happy as in this digital platform, we are able to interact with the legendary person of nonlinear fiber or waveguide optics, Professor Govind P. Agrawal, whose published books and research papers are really inspiration as well as motivation for all of us. We expect that the people who are working in the domain of nonlinear optics will be benefited a lot from his talk on space-time duality in optics and its applications. This session will be chaired by Professor Somnath Sarkar. Professor Somnath Sarkar is now a part-time member of West Bengal College Service Commission. He retired as professor from the Department of Electronic Science, University of Calcutta in 2015, where he joined in 1989 and served as head of the department for 2 terms. Then he was awarded the UGC Emeritus Fellowship in early 2016, and he continued his research and guidance in Calcutta University. Professor Sarkar has guided research leading to PhD degrees of 12 scholars and is still guiding 6 candidates. He is the associate editor of Advances in Optoelectronics and has published about 85 research papers in international journals of repute. It may be mentioned that he joined the fiber optics group of IIT Delhi in January 1982 under the Faculty Improvement Program scheme of UGC. His doctoral students are well established in India and abroad in reputed institutes. During his service period, he investigated research projects sponsored by AICT, CSIR, UGC, and also promoted teaching heading, DST Feast, AICT, etc. He is a reviewer of several prestigious foreign journals, including those of IEEE, OSA, Elsevier, and research projects of DST, CSIR. So he had been a nominee of DST and UGC and member of the peer team of NAC. I request Professor Sarkar to chair the session.
Thank you, Professor Maushumi Bose, for your kind introduction. And it is really a pleasure an honor to introduce Professor Govind P. Agrawal, who was awarded the most distinguished alumni award of IIT Delhi, my alma mater. So let me introduce him. Professor Govind P. Agrawal is a prominent name in the field of nonlinear photonics, fiber optics, lasers, quantum optics, silicon photonics. He received the MS and PhD degrees from the Indian Institute of Technology, New Delhi in 1971 and 74 respectively. After holding positions at the École Polytechnique Paris, City University of New York, and AT&T Bell Laboratories, Murray Hill, NJ, he joined the University of Rochester in January 1989, where he is currently the James C. Wendt Professor of Optics. Professor Agarwal is a life fellow of IEEE and a fellow of the Optical Society of America, USA. He has served on the editorial boards of many journals devoted to optics and was the editor-in-chief of the USA Journal, Advances in Optics and Photonics from January 2014 to December 2019. He chaired the USA Publication Council in 2009 and 2010 and was also on the USA Board of Directors during that period. Professor Agarwal received the IEEE Photonics Society's prestigious Quantum Electronics Award in 2012. He was the recipient of 2013 William H. Ricker University Award for graduate teaching. Dr. Agarwal was awarded the Esther Hoffman Miller Medal of the Optical Society in 2015. He was the recipient of two major awards in 2019, Max Born Award of the Optical Society and Quantum Electronics Prize of the European Physics Society. He has contributed a lot in several areas of optics, including nonlinear photonics, fiber optics, lasers, quantum optics, silicon photonics, and optical communications. He has authored 8 books, several of which are used worldwide for teaching and graduate education. His book on fiber optic communication systems is a standard graduate textbook in many universities worldwide for training telecommunication engineers. His book on nonlinear fiber optics was first published in 1989, and this book is very much helpful in training a whole generation of scientists and appears among the 10 top cited books in physics at Google. He has published more than 450 research papers in many international reputed scientific journals. We expect the researchers, scientists, faculty members, everyone will be benefited a lot by his speech today on the topic space-time duality in optics and its application. I invite Professor Agarwal to start his lecture. Before that, let me thank him again to see here and thank the organizers to invite me. And it is my pleasure to again cherish my memory with him when he visited my department 2008. And I remember that the basic merit of Professor Agarwal that he used to interact with the research scholars and share his knowledge and experience with them. I have seen that many big professors used to enjoy giving lectures of 400, 500 people. But I have seen Professor Agarwal mostly, I think it is true, Professor Agarwal, he mostly liked that thing. This I appreciated very much. And we enjoyed dinner with him, and that day it is a memory in life. And my scholars and Professor Mausumi Basu's scholars also interacted with him in 2008. And we have purchased a lot of books in the library, which is offered by him. So let me invite Professor Agarwal to deliver his invited speech.
Thank you, Professor Kar, for such a nice introduction. And I also want to thank the organizer of this symposium or webinar, especially Professor Basu, who contacted me and asked me to give this talk. So I am pleased to be here. Of course, could not come in person, but it is nice to be able to talk at least through the Google Meet, let's say. So let me share my screen now. So I will say present now, and I will share the entire screen. Okay, share the screen. Okay, so here we are. All right. So as you heard that today, my topic of my talk is space-time duality in optics and its applications. So before I start, I wanted to tell you a little bit about the historical introduction of this topic. And so it turns out that this topic was actually started in the 60s. Two people, one the French person Tournois in 1964, another Russian professor Akhmanov in 1969, noted that there is a space-time duality in optics. However, it was not, it didn't attract much attention, as very often the case for these things. And it so happened that about 25 years later, in 1989, two people in Canada actually first time introduced the concept of a time lens. And so they say the concept of time lens was introduced in 1989, and they used this concept to discuss what they call temporal imaging at that time. And this is the paper in 1989 that was published. And this has led to a lot of interest right away. There were publications by the same group. And later on, by now, this has become very popular, this topic. And some of the work has been done by my group. This is one of the paper we published in 2015 on temporal reflection. There have been discussion of ultra-fast time holography in this paper here. And I wanted to mention that if you are interested in this topic, then there's a tutorial that was published in 2014. And this tutorial is very, very useful to understand this topic further. So that's history. With that, let me tell you what I mean by space-time duality. You might be wondering what we mean by this concept. And the idea actually comes from a mathematical equivalence between spatial diffraction of beams and temporal broadening of optical pulses. To see this mathematical equivalence, one can write down the paraxial wave equation that governs the diffraction in one transverse dimension. And that equation, of course, we know can be written in this form, as we see down here. And this has only one parameter, k, which is just the wave number, or depends on the 2 pi over lambda. So this is a constant parameter, the wavelength, if you want. And this is a diffraction in one transverse dimension. I'm ignoring the y direction right now. So this is the equation, which is the paraxial wave equation. Now, similarly, if you go back and look at the pulse propagation inside a dispersive medium, and you assume that the spatial, nothing changes in the space, so it's like a mode is propagating, then you get an equation which looks similar to the other equation, but of course now x has been replaced with time. So the x and time has interchanged. And this is the space-time duality. And the only other difference is there's a one parameter in this equation, beta 2, which is known as the dispersion parameter. And it's a second derivative of the wave number with respect to frequency, if you want. So this is the only one parameter comes in. So these two problems looks identical, except with the sign changes you notice here. But beta 2 actually can be positive or negative. So this is the new thing, that this is the one difference, that beta 2, this parameter, dispersion parameter, can be positive or negative, while here the k is always positive. So in fact, there's more variety in the time domain, but the equations are identical. So that means many results from diffraction theory can be applied to optical pulses. That's the main idea here, that we can borrow concept from space domain to apply to time domain, and we can go in the reverse direction as well. And this is what people have been following. So with that, let me go to the next page here and introduce the concept of a time lens. So what is a time lens? So let's look at a spatial lens. What is a lens? Everybody knows the lens is just a glass made of glass whose thickness changes along the spatial direction x, let's say. And what does that mean? That means when a wave comes in, a plane wave comes in, it becomes curved. Its wavefront becomes curved. And so that means the lens is imposing a quadratic spatial phase shift of this form. Essentially, this is the idea here, that it is putting a phase shift which goes as x square divided by the focal length of the lens. Here, f is a focal length. So this is what it's doing. This is the input, this is the output, A out. It depends on the input, but you multiply by a phase factor, which is quadratic in x. So a time lens must do the same thing in the time domain. That means I should multiply my input by a quadratic phase factor, but quadratic in time. And now there's a parameter here, which is the equivalent of this focal length. I call it df. And it depends on the parameters of the device that you use to make the time lens. So basically, the idea is that as this pulse propagates through this time lens, it develops a curvature in time, if you want. It's a curvature in time, just like curvature in space here, or wavefront becomes curved if you want, but in time. So that's the point. And so that's what the lens is essentially. So now you're going to ask, how can I make such a lens? That is the next question you have to answer. It turns out it is actually very simple. You can introduce this kind of phase shift by a phase modulator. So phase modulator, as probably most of you know, is generally makes use of electro-optic material. So this is my modulator here. So I have electro-optic material, some is a lithium niobate, for example, and I can apply a voltage across this entire material. And this voltage, sinusoidal voltage, when I apply, then the phase of the incoming light gets modulated. So that's why it's called phase modulator. So mathematically, if you want to represent this device, you will say that the output amplitude becomes multiplied by the phase factor, which is changing periodically. The phase is changing periodically with time. So that is a new thing. I'm getting a periodic phase modulation. Now, you might say, well, this is not a lens. And you're right, this is not a lens right now. But if I put an optical pulse, which is much shorter than one modulation cycle, then you can think of it, then you can expand this cosine into a Taylor series at that point. And if you did that, then because the pulse will be much shorter than the cycle, overall cycle. So because of that, I can expand cosine, and I write in this form here. So now you can see the first term is a constant phase I can ignore. And second term has exactly the form I want. It's a parabolic phase with t square. And I can define a lens kind of a focal length kind of idea. And this will depend on these two parameters: how much phase shift I can produce, maximum phase shift, and what is the modulation frequency of the modulator. These two quantity tells me how much focal length, temporal focal length we want I can introduce with this. So essentially, by putting a modulator, and I can introduce a parabolic phase in time on the pulse. And this is like a lens, essentially, like this. So that's the idea. Now, the other techniques for making time lens. So basically, you can say that all we want to do is put a quadratic phase shift in time, which is saying what we call linear frequency chirp, because frequency chirp is just derivative of the phase. So essentially, we are saying any technique that imposes a linear chirp on the pulse will make a time lens. And you can do that many ways. You can do that by many ways. You can use it linearly and non-linearly. So nonlinear techniques can provide linear frequency chirp. For example, cross-phase modulation by a parabolic pump pulse inside an optical fiber will produce a linear chirp or a parabolic phase, if you want. Even you can use Gaussian pulses in the normal dispersion region of an optical fiber, and that can also provide linear chirp through optical wave breaking. This is known effect. And then finally, one can use a Fourier mixing inside a fiber or a silicon waveguide to produce this kind of chirp. So it's possible to use several nonlinear effects to make a time lens, but you can use a modulator and many other ways you can create this kind of time lens. So the question is, what can we do? We have a time lens, what can we do? So there we have to use the space-time duality idea and ask ourselves, what can a lens do, right? And we know what a lens can do. For example, we can take a lens and focus the beam to a small spot. I mean, this is what a focusing by lens means, that I can reduce the beam size by simply putting a lens here. So I should be able to do the same thing in time. That means I can replace this spatial lens with a time lens. So this is my time lens. And now I come in with a long narrow band pulse. So here's a pulse I'm coming in the input end. And this lens will chirp the pulse. That's what it's doing. So I get a chirp pulse, but it's still long. So now if I can insert a dispersing medium, just like here we were doing this diffraction, I do a dispersion, and this could be a piece of fiber, a piece of optical fiber of suitable length. I have to adjust the length to match the focal length of the time lens here. Then I should be able to compress this pulse to get a very short pulse at this end. So this is like a focusing by a time lens. So I can get a short pulse by this method. So a modulator followed by a fiber can produce a pulse compression. This is one thing we can say right away, which is useful for so many things. What else I can do? Well, if I can make a time lens, then I should be able to something what we do with normal lenses, we can make an image. So normal lenses essentially have a lens, and then you put an object at some place, and then you get an image at some other distance. So there are two diffraction in the input end and the output end. So I need a time lens, and I need two pieces of fiber or some dispersive medium. So this is my time lens. This could be modulator here. And then I have a piece of fiber on this side, a piece of fiber on that side. And if I choose the length right of the dispersive length of the fiber correctly, I should be able to make an image. So that means I can take some time-dependent variations on this side. This is my input, ultra-fast input. And I can go through this system, and the system will image this, this temporal profile to make a magnified form, for example. Now you might say, well, what's the point of this? I mean, compression, a lot of people like. Why would you like to magnify? I mean, actually, there are practical reasons. Short pulses are very hard to measure. You can use autocorrelation, but you don't get actually the pulse shape. So it's shape of the pulse is very hard to measure normally for short pulses. So if you can magnify them by a factor of 10 or 100, then you can just use a detector to detect them. And if you need the magnification factor, you can conclude what the pulse width would be, but you get a pulse shape. Exact pulse shape is reproduced. So this has useful. This kind of temporal imaging has used for that reason. And it turns out that the imaging condition is exactly what you use for a lens. 1 over u plus 1 over v equal to 1 over f. And that's the imaging condition for this temporal imaging. And these are the parameters for d1 and d2 depend on the dispersive medium. Parameter is length. So beta 2 times L is this d parameter with a unit of picosecond square, for example. And the df is the focal length of the time lens, for example. And so if you mesh this condition, you get the same kind of condition to make an image. So that means you can actually make a time microscope with this device. So that is the next thing I want to show you, that this is a time microscope or temporal microscope. So essentially, this is an imaging system. So what we have here, we have this is a spatial lens, and then my object is on this side here, and I get my image on that side here. This image can be inverted sometime, as we know, can be magnified. So same thing would be here, that I can use a time lens, and I can use two dispersive media, it could be optical fibers, and I adjust the length right correctly. Then I can take an input pulse or input time varying input, and I can create a magnified output at this end. And the magnification factor M would be just like here, as it depends on the distances of the input and output end. This will depend on the ratio of this D parameter for the input and output end. So you can control this to get a larger factor. And just like here, you can invert an image, I can invert the shape, essentially. You get an inversion of the shape as well, here. So it follows. Everything you can do with a lens in space can be done with pulses in time, essentially. That's the idea here. Okay, so that's useful. That could be quite useful for something. But something else you can do, which it turns out is even more useful, is called temporal Fourier transform. Or sometimes people call it dispersive Fourier transform. This has a lot of applications, and I want to focus on that a little bit now. So let me first introduce the concept. The concept is actually very simple. If you think of a slit diffraction, let's say I have a square shape input beam, and I diffract it. Then if I go to far field, I have a long enough distance here, then in the far field, the shape I get of this beam is actually Fourier transform of the input shape. So in other words, I can create a Fourier transform of my any pulse shape I have. I should be able to create a Fourier transform by simply diffracting a beam and dispersing a pulse, for example. So if I take a long piece of fiber, that means I satisfy this condition, that the dispersion of this fiber is length is long enough that this condition is satisfied right here. So in that case, I should be able to take a pulse and create this Fourier transform at the other end. The spectrum will not change. The spectrum does not change, but the shape of the pulse will evolve and take a shape which looks like a Fourier transform. So this is useful. I can make a Fourier transform and has a lot of applications. I will come back to this in a minute. Before I do that, I want to talk about something known as 4F processor. So in a space domain, people talk about signal processing, optical processing. And that essentially means that they use what we call two lenses, which are spaced apart by 2f. F is the focal length. And then you put the object on one side and the image on the other side. And this creates this is called 4f processor, because total distance is 4 times the f, if you want. But the point here is that in the Fourier plane, you create a Fourier transform of the input. And you can do processing here. You can create some sort of mask at this plane to modify the Fourier transform, and that will change the image accordingly. So this is called a processor, signal processor, if you want. You're processing this signal. And this has a lot of applications for image processing, for example. So we should be able to do something in time. But problem is, of course, that if you want to implement in time, I need to have 2 time lenses. So 1 time lens, 2nd time lens. And then I will need 4 pieces of fibers of suitable length and dispersion. And then I can mimic the same thing, because I have a Fourier plane. I will get the Fourier transform of the input pulse, and I can put some sort of mask here, and then I can come to this end, and I get that. So you can recreate a 4F processor, but it looks very complicated, essentially. So, but turns out actually you can do much simpler. And much simpler is shown here. And you can make it much simpler because, as I told you a minute ago, that if you take a long piece of fiber, a long piece of dispersive medium, then I can create a Fourier transform without needing a time lens. I don't need a time lens. This fiber itself will produce a Fourier transform. So I can do my processing here, and then I can go back to time domain by simply using a fiber with opposite dispersion. So if I have a positive dispersion here, I need a negative dispersion here to bring back the pulse back to time domain. So that's the only thing I need to do. So this is a much simpler Fourier signal process, a Fourier processor, because I just needed 2 pieces of fiber. I just needed 2 suitable pieces of fiber to do my Fourier processing. So clearly, it's very nice, very easy thing to do in this case. Now, we can't do this in space, by the way. We cannot do this, what I'm doing in time. I can do in time because I have possibility to change the sign of the dispersion parameter. In the case of diffraction, I cannot do negative diffraction. There's no such thing. And that's why I need to do this more complicated thing. But in this time, because we can change the sign of dispersion parameter, it's possible to make a Fourier processor by just using 2 pieces of fibers. You can do that. So it's very popular, very, very useful. Okay, so it turns out that dispersive Fourier transform, the property that I can create a Fourier transform of the input pulse in time. Essentially, this is in time, but this is Fourier transform. So that means my shape of the temporal shape of the pulse mimics the spectrum of the pulse, right? So this is what is happening. I mean, if you look at this process here, and this is from paper from Jalali's paper in 2013. So I have a pulse in time. It's a short pulse, but it has a broad spectrum. So as this pulse goes through the fiber, it broadens. Remember, dispersive media broadens the pulse, but it does more than that. It actually chirps the pulse. And chirping of the pulse actually creates different frequency component along different part of the pulse. And because of this process, at the end of the fiber, what I get is a pulse shape that mimics the spectrum. Okay. So you might say, well, okay, I got a pulse shape that is spectrum. What good is that? Well, what good is that? You can measure the spectrum by simply using a detector and an oscilloscope. You can get the spectrum, right? That's what you can do. So you will say, well, I can do that with a spectrometer. I can use a spectrometer. I can do that. It's not the same thing, by the way, because a spectrometer will never create a single shot spectrum. A spectrometer takes time. It has a grating inside. That grating has to turn. So if you have a short pulse, you cannot measure a spectrum with a spectrometer, a monochromator, but sometimes we call it, because it has to average. It will take average over many pulses. You can only get the average spectrum. If the spectrum is changing with time, you can never measure it with a spectrometer. But here you can measure it. With this method, you're creating a snapshot of the pulse at the detector end, and you can display on an oscilloscope. And now if the spectrum changes in real time, you can see in real time on an oscilloscope how it changes. So this is very useful, by the way. This is a really amazing device. Just a piece of fiber, by the way, nothing much. It's a very useful. So it's valuable in areas such as sensing and medical imaging. So I will show you one example of medical imaging so that you can see why it is so valuable. So for example, let's say I have a short pulse. So application of DFT. So I'm doing a medical imaging application first. So I have a short pulse with a wide spectrum. Okay, so here wide spectrum. I sent this pulse through a sample. And this is some kind of medical sample. So I take here I'm just showing you something. But the point is that there are different kind of molecules here. These molecules absorb different wavelengths. So because of that, when you come out, you actually get the molecules image imprinted on the spectrum. Because different places will absorb different things at different wavelengths. So you actually get some kind of imprint on this. You find that this is actually in time still, but the wavelength has. So this is basically what we're saying. Different wavelengths are being absorbed differently, essentially. Okay. So now this is a spectrum has been modified, and it has information about the sample, right? What do I do next? I can put on a dispersive element, which is a long piece of fiber, for example, and this will change the pulse shape, and the pulse shape now will mimic the spectrum right here. So shape looks like exactly this shape. And now I can put a photodiode and I can measure this shape. So that means I can get information about this real time, what is going on, and the different location of this, different distances here will tell me what molecule is located where, essentially, on this end. And now because I can measure in real time, if this molecule is changing in time, I can record that on the photodiode. I will see that on the oscilloscope. I will see in actual time the image of the sample, if you want, in some way. So this is essentially encoding, spectral encoding of the information that you are using to make an image, if you want. Same thing you can do, for example, for telecom application, other things, the same thing. You can take a pulse with a wide spectrum and use a spectral filter. This could be a grating, this could be something that will produce or some other thing that will modify the spectrum. And then you can measure that spectrum in real time. And so this can be used for sensing, for example. So this is very useful. I mean, this is one idea of making a Fourier transform very useful. I've just mentioned one more thing before I change to different topic. And this is that you can actually make a system where you change not only the Fourier transform in time, mimic a spectrum, but you can also reverse so that the pulse shape, input pulse shape is now reflected in the spectrum on the other end. In other words, you can reverse both time and frequency shapes, which they get totally inverted in this case. And so this all requires a lens, for example, and then you need a dispersive medium with opposite dispersion parameter, beta 2 times beta 2 and minus beta 2. If you do that, then you find that this device will invert the spectrum and the mirror, and the spectrum and the shape in actually. So the shape at the output will mimic the spectrum, and the spectrum at the output will mimic the shape. So you will say, well, what is used for that? Well, this has been being used nowadays for telecom application. So for example, you can do what we call WDM to OTDM conversion or vice versa. So for example, you may have a time domain multiplexing signal in time domain, and you can make it a WDM signal if you want. So that's one possibility. Here's an example, just to show you one example. So here is an example where we have a 160 gigabit time domain signal. So this is OTDM to WDM conversion. So I have a 160 gigabit OTDM signal coming in, and then I mix it with a pump, and these pump pulses are chirp. That's why they look tilted here, these chirp pulses. And because of that, I create now I do Fourier mixing, so I create an idler. And this idler has now multiple peaks. And these peaks actually are correspond to different channels. There are 16 channels here. Those 16 channels have been converted from time domain to spectral domain. So this become OTDM to WDM. And it turns out that this is exactly contains information of 16 channels that you had in the original time domain signal, essentially. So this is a very useful device. And you can do reverse process. I'm not going to spend time on that. So let me now move to a totally different topic that we have been working for about 5 years now. And this has to do what I call temporal reflection and refraction. Okay. So everybody knows what happens in space. In space, if a pulse or reflection and refraction of optical beams at a spatial boundary are well known. Right? So I have a spatial boundary here, and my beam is coming up from the top. When it hits the boundary, part of it gets reflected, part of it gets transmitted. And you know, Snell's law will change the angle. So angles are changing. What does that mean? Angle actually means the photon momentum is changing. The angles relate to k vector, and k vector relates to momentum. So if the photon momentum is changing, you can change the photon momentum at a spatial boundary, but not frequency of the photon or energy of the photon. So frequency is conserved here, but you can change the momentum. Why? Because you have a spatial discontinuity. A spatial discontinuity quantum mechanics implies momentum is not conserved, essentially. Space and momentum are conjugate variables in quantum mechanics, and hence you can change the momentum, but you cannot change the energy. So frequency is conserved. Okay, so we can now ask, with this understanding, I can ask, what is the temporal analog of this optical phenomena? What is temporal analog? So it's again space-time duality. So what happens when an optical pulse arrives at a temporal boundary, across which refractive index changes suddenly? In other words, I have a boundary in time. That means at some time before, refractive index has some value, but then after this time, refractive index changes, has different value. So it's temporal boundary. So what will happen? Now, as I said, a spatial boundary, frequency is preserved, but momentum can change. But in the quantum mechanics, or in general, at a temporal boundary, momentum must be preserved, but frequency can change. So I expect that this, when this in time domain, when this happens, the frequency of the pulse will change, photons will change. So I will change the spectrum of the pulse if you want, but I will not change the momentum of the photon. So the k vector will remain conserved, essentially. They must conserve. So a change in angle in spatial interface translates to a change in the frequency of incident light. So this is the fundamental point here, that when I have a discontinuous time, I will change the frequency and not the momentum. Okay, so that's I think that should be clear with that. So this is again showing a space-time duality idea, that in space I can change the angle when I come from two media of different refractive index, but in time when I do the same thing, I change the frequency, but not the momentum. So my momentum will be conserved, but here the frequencies are conserved. In the spatial case, now the momentum is conserved in the time case. So I will use this argument to really figure out what to expect and how much spectral shift you can get. So let's look into that a little bit more. Okay. Now it turns out that it's very hard to change the refractive index everywhere in space, because that's what we were talking about that. So it's much better to consider a moving boundary, moving temporal boundary. So reflection at a moving temporal boundary, let's look at that. So what we are saying now is that here is in the lab time, my pulse is moving and my boundary is moving. They both are moving, but let's say my boundary is moving faster than the pulse or slower than the pulse will hit the boundary. And hence it will get partly reflected and partly transmitted. Now, if I change this picture in a moving frame in which boundary is stationary, then this will look like exactly what you expect in space before, that I have refractive index are different on the two sides, and my incident pulse gets partly reflected, partly transmitted. So from now onwards, I'm going to work in a moving frame in which the boundary is stationary. So my time is now defined a little differently. I'm artificially making my boundary static just to do that. But remember, in reality, both the pulse and the boundaries are moving, essentially. That's what we're going to do. So let's look at this case and see what we can expect. Okay. So here is an example of a simple model of pulse propagation in this case, for example. So let's assume the optical pulse is propagating inside a waveguide with some dispersion relation beta omega. Okay. Now, temporal discontinuity at t equal to tb, at some time there is a discontinuity, and this is my location boundary. I incorporate that by using this dispersion relation. So this is the most important equation is this, essentially. I can't select it. So, okay. So what I did here, I'm adding this Heaviside function, which is the step function. So I'm saying at t greater than tb, my refractive index becomes larger. So that's my beta becomes larger by some constant amount. So this is my temporal boundary right here. And this is my dispersion, and I'm including only up to beta 2 terms, so quadratic dispersion relation. You can include higher order terms if you want, but I'm going to stay with beta 0, beta 1, beta 2. Of course, delta beta 1 here is the relative speed related to the temporal boundary. So this is a mismatch, sometimes called differential group delay, sometimes called this quantity here, delta beta 1. So that's what we are saying, and then as you see here, so main thing is that this beta will change over here, remember? But now we said my momentum should not change. As I cross the boundary, momentum should not change. So how would I preserve the momentum as I cross the boundary? The answer is will change the spectrum of the pulse. That's how it will increase the momentum. So if the refractive index changes, then beta B is just kg to delta n. And so you can now use this dispersion relation to investigate what happens to the pulse when it hits the boundary. So pulse propagation. So let's look into that. So this is I convert the dispersion relation into a equation for the that is satisfied by the pulse, and this is what you get. This is well-known equation, and this is my temporal boundary effect. At a certain time, I change suddenly the increase the refractive index, or increase the beta. So we solve this equation on the computer now, and we assume the input pulse is a Gaussian pulse of some width. You choose that width to 1 picosecond for the time being. I'm assuming my boundary is located at 5 picoseconds. So because the delta beta 1 is not 0, so I'm going to take it some value. So my pulse and boundary will approach each other. And there is some dispersion in the medium. And this is my change in the refractive index. Now I want to just tell you the parameter I'm using here. It corresponds to a refractive index change of only 2 to the power 10 minus 7. So this is I'm not asking for a huge jump in the refractive index. It's a small change in the refractive index at the boundary. That's it. Okay, so we can solve this equation and see what we see on a computer, basically. So that's what I'm going to show you now. Results are coming out of this. So the result you find is this. And this is a paper we published in 2015 in Physical Review Letters. Essentially, what it's showing you here is that this is my input pulse. So let me go back here. So my input pulse comes in, and this is the input pulse, and it's traveling into the medium. And this is the optical fiber. I'm taking medium. So distance is 100 meters here. And this pulse is moving slowly and approaching the boundary. Boundary is fixed here. The refractive index will change after this. So it's going to hit the boundary, and it hit the boundary, part of it goes through, part of it gets reflected. Now, reflection here is not very large. It's about 1%, maybe about 1 or 2%. It's not very large reflection, but there's a reflection. So if you look at the spectrum here, what happened to the spectrum? My input spectrum is located here in this spectrum here, this yellow, bright yellow line. But as I cross the boundary, I get a spectral shift. The reflected pulse gets a lot of spectral shift. The spectral shift is very large. It's about 6 or 7 terahertz spectral shift for the reflected wave. And the refracted pulse get a small phase shift. So both of the spectral shift takes place for both reflected and refracted pulses. We see that right away at the boundary. Just at the boundary, there's a big change in the spectrum. And this is what we expect, by the way. This is what we expect, that in order to match the momentum conservation, I would have to change the spectrum. And this is exactly what you see here. So this comes when you solve that equation on a computer. Now, we can look at the same thing by making spectrograms. That gives you a little better picture. So spectrogram for 8 picosecond Gaussian pulse. So when you make a spectrogram, so I'm plotting the time on the vertical and the spectrum or frequency on the horizontal. And so if you plot this, changing in color, right? So in these plots, a pulse looks like a bullet, essentially. That's why people like to make this. So the spectrogram, basically time and frequency are plotted at the same time. So I'm getting some kind of bullet-like a situation. And this bullet will move towards the boundary. Boundary is located somewhere here, somewhere around here, over here. So this bullet starts moving towards the boundary. It's moving, and now it hits the boundary. The boundary is 30 picoseconds. So it hits the boundary. And as it hits the boundary, you can see that it's creating it's going through it, but it's also being reflected here. And you can see more clearly here. Most of it got gone through, but there's a reflection. And now notice that the reflection is moving backward. It looks like moving backward, but in fact, it's not moving backward. Everything is going forward, by the way. It appears backward because I'm a moving frame. It's because my boundary is also moving. So what is happening is it's moving slower than the boundary at this point. So reflected pulse is moving slower than the boundary, and hence, why is it moving slower? Because I changed the spectrum. And there's a dispersive medium, speed depends on the frequency, so that's why it is moving slower. Okay. And my transmitted pulse is moving faster than the boundary. That's why it goes to the other side. So nothing is moving backward here, everything moving forward. My pulse is moving, boundary is moving, my reflected pulse is also moving, transmitted pulse is also moving. But the spectrum I'm changing at the boundary. That's what is happening. Okay, so the question is, can I calculate the spectral shift? And the answer is yes, you can calculate the spectral shift by just using the momentum conservation. So conservation momentum is shown here. So blue curve is for t less than tb. So t less than, before the boundary, I have this blue curve for this person. It's a parabola. After the boundary, I get a green curve. So after the boundary, I get a green curve. Now, if I consider, if I look at this quantity here, and I say that I want to preserve my momentum, so this is my input spectrum, and it's covering this range here. And now, if I take it as a central part here, so this is my central frequency component. And now I have to move to this curve and conserve the momentum. So all I can do is move this point to this point here, what I call 1. So that will be my refracted or transmitted pulse spectrum. And then the second solution will come here, over here, which is the reflected pulse. This solution is not realistic because it has a change in the slope, and we can't accept that over here because so this is the real solution. 1 and 3, those are the real solutions. So we can now use our dispersion curve to calculate the spectral shift for these two. And it's not very hard. You can write down the dispersion. You can write down the dispersion relation again, and you can say, well, for reflected pulse, this term is not there. In the first medium, this will be 0, and you can solve this quadratic equation and you find the frequency shift. So this is shift of the frequency. What is shift of the reflected pulse? And this can be very large, by the way. If you look at the number, plot the number here, this shift is several terahertz typically. It's a large shift for the reflected pulse. On the other hand, for the refracted pulse, if you solve this equation with beta b here, and this becomes 1 after the boundary. And if you solve this pulse, so this is the phase matching condition, you solve this, you find that the transmitted pulse now looks very, this is the shift you get. And only plus sign corresponds to physical solution. So it tells you there's some shift, right? You can use a plus sign here and find out. Now, there's just some funny thing here you might notice here a little bit. If this thing in the parenthesis here under square root of sign becomes negative, suppose it becomes negative, if parameters are such that this whole thing is negative, then omega t does not exist. And this is actually what we call total internal reflection. In other words, if I can make this 2 beta b beta 2 over delta beta 1 square more than 1, that means I need more in the exchange clearly to make it more than 1. Then at that point, the transmitted pulse does not have a solution. So only the reflected pulse will exist. And that's total internal reflection. So we see from the solution that there is a total internal reflection. And but we find that that's exactly true. This is what I'm telling you there. So this is the condition. If you satisfy this condition, you get total internal reflection. So let's look at what we find. So we go back to computer and solve it again. And it turns out that you can get it in the both normal and anomalous dispersion region because all you have to make sure that this condition is satisfied. And you can get into both cases. So here's an example of that. So again, I have a Gaussian pulse coming in, and this pulse is hitting this boundary. And now I have made my index change large enough. And that means about 10 minus 6. I'm not making it very large. If this is large for this system here, if it is up there 10 minus 6, then I satisfy the TIR condition, and I can actually get 100% reflection. And so this is what we mean by you can get a total internal reflection. And if you look at the spectrum, as what you will expect, suddenly the entire energy of the pulse get transferred to a new place, and this is about 6 terahertz away. So then complete energy transfer to the reflected pulse is taking place at this point. So this is pretty interesting in that sense. Also, if you look carefully here, it's not obvious here, so I'm magnifying this part here. You can actually find that there are fringes here going on, and there is some light on the other side. So this is actually what you expect in the space domain. There's an evanescent wave on the other side, which lasts only for a couple of wavelengths in space. So it lasts for a short time, but there's an evanescent wave. And the surface wave is created, if you want here, something. And then reflected and an incident pulse interfere with the different frequencies to get these fringes, essentially. So these fringes are because I'm interfering two pulses with different spectra. So those are this, and you can see that there is some kind of going on the other side. So this is interesting. It's exactly what you expect. Whatever happens in space, it happens here, right? And there must also be a Goose function somewhere here for the same region. Okay, so this is now a spectrogram for 8 picosecond Gaussian pulse, showing a total reflection. This is my input pulse, approaches the boundary, hits the boundary, and nothing crosses the other side. Everything remains on the same side, and now it just goes slower. And this is total internal reflection. Nothing is leaking to the other side. So this is all coming out of solving one equation over there. Now you can ask yourself, what happens with third order dispersion? Well, if you have third order dispersion, you have to include this cubic term into, so third order dispersion requires this cubic term has to be added over here with beta 3. And so dispersion relation now are different. So for example, the dispersion relation before the boundary is this. After the boundary, it becomes green curve over here. And so question is, what would that do? What would that do is that can create more than one solution. So in other words, you can have a double refraction and reflection in this case. And this is something I don't think we have seen in the lab yet, any of these things, but you can see that you can create two transmitted pulses and one reflected, or you can go vice versa sometimes. So in everything, both of these are possible scenarios because there are multiple solutions over here. It's a little more complicated, but you can see spectrum is changing, getting multiple, the 3 solutions sometimes. So here there are 2 reflections, here there are 1 reflection and 2 transmission kind of things. Okay, so the next thing we ask ourselves, can we make a temporal waveguide? In other words, if I have a region where the refractive index is different, and it could be lower, by the way. So in other words, I can have a situation where I have a high index and a high index on each side, but in the middle, I have a low index. Now, spatial total reflection cannot happen because you have to go from high index to low index for that to do, but in time, you can do both. It could be higher in the middle or lower in the middle. You have to change the dispersion of the medium to get this going. So either way, you can have a situation where something gets trapped inside this this little well, if you want, in this case. So you can trap the pulse inside here. I mean, you can expect because each side you get total reflection, and hence the pulse cannot leak through, essentially. So to do that, we first of all ask ourselves, are there waveguide modes, temporal waveguide modes, essentially? In other words, we solve that equation and ask ourselves, are there modes in this problem? And we found there are modes, just like modes, spatial waveguides are modes, temporal waveguides are modes. And the number of modes depends on this V parameter, which in this case is, of course, defined very differently than in the spatial case, but there can be multiple modes. And this is an example of this mode, fundamental for 1 mode, 2 mode, 3 modes, for example, or the third mode, essentially. But these are the different modes of the system exist. So essentially, when a pulse will come in, this is going to couple into these modes, and that will determine what happens to the system as such. So here, example, for if a nearly single mode waveguide, so I have a 2.5 picosecond pulse, and my window here is 10 picosecond wide. So I'm coming with a very narrow pulse, but the window is actually larger size. So of course, I'm not matching, I'm mismatched. So because of that, I can confine the light, but I also lose a lot of energy on the outside here, you can see here. So if I increase the pulse width, 5 picosecond means the full width half maximum is about 8 or 9 picoseconds, so it matches pretty well. So in that case, you can see the almost entire energy of the pulse is confined to the waveguide. So there's a question of mode matching, but if you can do mode matching correctly, you can make a single mode waveguide where entire energy of the pulse can be coupled into a single mode of the waveguide. So that's interesting. Now, if you're a multi-mode waveguide, in that case, of course, what happens is something you would expect. I mean, if I have a short pulse here and my width is very wide, and it's a multimode waveguide, then of course I will go up first, hit this boundary, and I will get reflected. So I will come down and hit the boundary again, come down again. So I get multiple reflection, and refraction will take place. And every time when you hit the boundary, you change the spectrum. So you go from here to here, and then come back here, you go back to original spectrum. So you can see that as it is bouncing back and forth, it's shifting its spectrum each time as such. So essentially, it's a usual picture that each boundary is confining the pulse to in the center, say, for that region. So that's something you can expect. So I think I gave you some of the ideas here that what we can do. So nowadays, we are actually working on it in the lab to see some of these effects. So to make a waveguide, temporal waveguide, I need to have two moving boundaries. How can I have this? I can do that. There are two ways I can do that. I can either send a microwave signal to create a refractive change inside the electro-optic modulator. For example, you can send a square shaped microwave pulse that will increase the index only under the microwave. And this microwave will propagate. And then you can send an optical pulse inside the waveguide. And then you can arrange situations such that the two hit each other, essentially. Your pulse enter this or inside this region, and we eventually can be trapped. So essentially, you can use a microwave signal to create a refractive index window or a different window of high index, for example, let's say. And that's one way to do it. The other way to do it is that you can use a cross-phase modulation inside a nonlinear waveguide. So this could be a fiber if you want. And so what we are saying now is as a pump pulse goes through the fiber, everywhere the pump pulse exists, refractive index is larger because of the Kerr effect. I create refractive index. So I create a window of a larger refractive index through the pump pulse. And now I can have a probe pulse inside this window. And if I adjust the condition right, this probe pulse can never leave the window, essentially. It's confined by the window. So that's another way of doing it, kind of. So two ways. I mean, you can either use a microwave signal with electro-optic modulator, or you can use pump probe in a waveguide kind of idea. So here is what we did, some simulation for it. So this is an example of that, how you can do reflection. So I can, for example, send a soliton, for example, and reflect from a soliton is possible. Or I can send a very broad pump pulse, and I reflect from one of the edge of the pump pulse, like that. So this is a single reflection. And this is another example of how can a single soliton, for example. This is my pump is a short soliton, and the probe is coming in, hitting the pump. This is like a wall boundary, and you get reflected and refracted, for example. So this is some of the ideas. Or you can make this multi-mode waveguide. So you can have let's say input pulse is a rect pulse, pretty much. So pump pulse is broad, a rect pulse, so 20 picosecond super Gaussian pump pulse with 10 watt peak power. And we assume dispersion is 0 for this pulse. So this creates now a window of high refractive index. And then I can put a probe pulse inside it, and then I see if it's confined or not. And this is what we find on the computer, for example, that I can easily make the probe pulse hit and come back and go that. This is exactly what we were talking before, that they cannot leave this window or this boundary, essentially. So in principle, you can do this, it looks like. Single mode waveguide also you can do that. So if your window of the produced by the pump and the probe are roughly same size, then you can confine the probe to the entire window, and that can be done too. So all of this which we discussed seems to be possible in principle. So as I said, these days we are working in the lab and try to see some of these things, and hopefully we will have some results soon. Because of this COVID, actually lab work stopped for quite a while. I think that created a lot of problem for us. But anyway, we are back there now. So let me conclude with this. I think I gave you a lot of ideas here, but the main idea here is that space-time duality is a simple concept with many applications. Okay. It can be used for temporal imaging and for making time microscopes. I told you that. Temporal equivalent of total reflection occurs for optical pulses at a moving temporal boundary. Okay. And important point to remember, in the temporal case, frequency shift plays the roles of angles. That is because of the momentum conservation, energy conservation argument. the found conditions under which an optical pulse can be confined to within a temporal waveguide. We also found the modes of these waveguides analytically. In a single mode condition, was you can find that. A pump drop configuration can be used to make such waveguides through the knowledge of phenomenon of crosswave modulation. So this is sort of easy thing to do in the lab. So we are working on that right now. So with that, let me stop this over here and take any questions you might have at this point. So I will start.
So thank you, Professor Agarwal, for your nice and illuminating lecture. So now I request Professor Mausumi Basu to just open the chat box and place the questions before Professor Agarwal. And I will then ask questions. But I will also require the research scholars, especially working in this field, to just use this occasion to just have a couple of exchange of their ideas with Professor Agarwal, because he is really fond of exchanges of ideas with the research scholars and enrich ourselves. Please, Professor Mausumi Basu, carry on.
Yes, there are so many questions, at least 20 questions, 20 to 25 questions.
Okay.
So, first question is from Devanshu Garg. Sir, what does this compression does to amplitude of the pulse? So this was relating to that time length probably.
Right. So this is related to the temporal focusing by a time length, essentially.
Time length.
Right? Yeah. So what's the question? Can you tell me again what is it precisely?
What does the compression does to the amplitude of the pulse?
Yeah. So with the time length compression, you actually reproduce the same pulse shape as the input pulse, but compress it. And so because the energy is conserved at the same time, its amplitude will go up clearly. I mean, the energy is conserved. So amplitude will become much more intense, but the shape will just scale. It's scaling essentially in this case. You multiply the entire pulse shape by scale factor essentially. And that scaling is like a magnification factor, but magnification factor is sort of here less than 1. So you multiply by that factor. So whatever pulse you have, you multiply by scale factor in time, and you get a new compressed pulse in that way essentially. But its shape will remain, everything remains same, but the scale becomes smaller. And similarly, when you magnify the pulse, you multiply by scale factor. That's that. Now, of course, that will change the amplitude. It has to change because energy has to be conserved.
So next, another question from Titash Dash through YouTube. Does the magnified output include any kind of distortion?
In reality, yes. I mean, if you have perfect lens, I mean, that is a very idealistic situation. We can make a perfect lens, time lens, then you can probably do it without distortion. But in practice, of course, a lot of things will be there that will distort these things essentially. Depending upon how you make this lens. I mean, if you make a lens by using modulator, then you have to worry about the fact that it's parabolic only the center part of the pulse, and the modulation cycle actually a cosine function. So the wings are not right. So unless you fit the pulse in the center part of the modulation cycle, you'll have distortions. I mean, clearly. Similarly, if you use a fiber or something to make this time lens, then you have to worry about the higher order dispersion effect, beta 3 and things like that. So in practice, of course, it will never be perfect. There is some distortions, but you can come close to it. You can get a nice thing, but I don't think you can avoid distortions in practice. In the lab, we will have some problems. Yeah.
So time lengths cannot be used for the higher order dispersion concept compensation.
No, the higher order is always creates distortions. Higher order dispersion, you cannot. Anytime you have a beta 3, beta 4, higher order term, you get distortions. I mean, it just requires quadratic term. It's the one which is required.
Professor
So
Basu, there is
quadratic
another
things
question. Another question from Shostik Bollov. You missed it. So.
Okay.
What will be the limit of input pulse to compress in such a way?
So input. So first of all, the question is, what is the magnification factor or compression factor you can achieve in practice. I would say a factor of 10 is already a large. I mean, practice is very hard to get more than a factor of 10 compression or the broadening. I mean, either way, either direction. So factor of, if you work very hard, you might get a factor of 10, but even that will be hard to get. So generally, you can probably go down by a factor of 4 or 5, but not much more than that.
So will the peak power or intensity of magnified pulse remain same?
No, as I said that because if you are taking a single pulse and you are trying to compress it, energy has to remain, energy is conserved. If you are not losing much energy, might lose some energy, but you're not losing much energy, and hence the peak power has to go up, essentially. The amplitude will change, yes. But the shape will be same. Shape is like a simulaton. You're stretching, it's a stretching and compression, so essentially shape will not distort, but the peak power will go high, yes.
So in this spatial 4F processor, we physically include spatial masks on the central plane. How is the same done for temporal?
So same thing. You can, so in the temporal case, you are making you have a place where you have some sort of spectrum is coming in. So now you can either put a phase profile in time. Essentially, you put something that will induce a time-dependent phase shift. Because different time is frequency is changed to time. I mean, your spectrum is mimicking spectrum, but it's still in time, right? So what you can do, you can actually either pass this beam through a spatial modulator or something, but generally what you will do, you will produce a phase mask something, but it will change in time, essentially, if you want. So you will do some sort of temporal modulation if you want. And that will modulate different part of the spectrum differently. But we are doing in time. Remember, we are not going to frequency domain. We are changing the pulse shape so it mimics the spectrum, but we're still in time domain, by the way. So when we are doing processing, you have to apply some sort of phase, which is time-dependent phase to it. You pass through a system which apply a time-dependent phase, it could be modulator if you want, and that will sort of put either different losses for different frequency component or different phase shifts, and then you come back and see what happens. So essentially, in practice, what happens is that you will try to see what you want in the output, and then figure out what exactly kind of mask you need, and then develop that mask using a modulator or something. It has to be in time domain, essentially. Okay.
Okay. The next question is from Chirag Arora. Can DFT be used to see dynamic changes in the spectral profile of the molecule, as it can be used to see how the spectral evolution is taking place as the molecule shows dynamic effects?
Yeah, so if the molecules move, if the molecules are moving, then when the pulse is crossing, it will be a different place. So it will come a different place into that. So the location of that dip in the spectrum I was showing you will change essentially because the molecule has moved, and hence the location, when you look in the time domain, the stretch pulse which shows the spectrum, different location there corresponds to different location in the space of the actual molecule. So you can infer the location of the molecule by looking where the dip is happening, where the spectrum absorption took place essentially. So in practice, this can actually, you can make a movie out of it, that you display the spectrum on an oscilloscope, and as the molecules are moving, this pulse shape will change on the oscilloscope, and you can then write a computer program that can translate that into some shape of the molecule you want, kind of different structure. So you need some sort of software that will take your temporal information and convert that into a spatial information at that point.
So there must be some correlation between these.
Yeah, there's correlation. Yes, exactly right. Yes. Right.
So won't the refraction at temporal boundary follow Snell's law?
No, it has its own Snell law. It is not the traditional Snell law, because spatial Snell's law has the angles into it, and we can't use that. But we can find a temporal version of that which will have frequencies, not angles, essentially. So you can come up with the reflection and transmission coefficients and the other things. The shifts I told you, those are corresponding to Snell's law, how much shift you are getting. So like angle change, Snell's law tells you what is the angle change. And what I showed you here, frequency shift, is kind of Snell's law. I mean, because it tells you how much frequency will shift at the boundary, essentially. So that is a kind of Snell's law. So Snell's law does not hold in regular form. A different Snell's law holds if you want.
So Dr. Sampath Mukherjee from our department, does the phenomena depend upon smoothness of the boundary which separates the two media?
Oh, of course, a lot. It does depend. I mean, so most of the time we are assuming very sharp boundary. Of course, nothing is very sharp in reality. So in reality, of course, your refractive index will change over some time period, essentially. So in general, if this time period it has to be faster than the pulse itself, the pulse rise time and something like that. So working, let's say, with a picosecond pulse, let's say 5 or 10 picosecond pulse, then the sharpness of this refractive index boundary has to be of the order of maybe 100 femtosecond. So you have to change the refractive index over the duration 100 femtosecond or something like that. And that can be done with huge pulses. Or pump pulses can be short boundary, you can make that. Or in time domain, if you're using a modulator, then it's very hard to get a modulator with more than 40 or 50 gigahertz bandwidth. So that means there the scale at which you can change this boundary is about 20 picosecond, if you want. And so if the boundary change is 20 picosecond, that means you will have to use pulses which are 100 picosecond or longer to get your things going, essentially. Otherwise, this effect will not be there. So yes, the answer is sharpness of the boundary is critical. If the boundary becomes very shallow, the reflection disappears. That's the answer.
So what next question from Monica Pradhan. What are the limits for calculating the spectral shifts?
So spectral shift comes out of comes easily if you mesh the what do you call it, momentum conservation. If you take the propagation constant, you insist that should not change as you cross the boundary. That is what we use to calculate the spectral shifts, essentially, for the reflected light. So there is a very simple equation you can solve and get the spectral shift. And the spectral shift depends on dispersion of the medium, of the fiber or whatever you're using. It depends on the relative speeds of the group of the pulse with respect to the boundary. So the speed mismatch with the boundary and the pulse plays a big role. So two parameters those are important are the dispersion of the medium, speed of the boundary with respect to the pulse, and I think those are the two, and how much index you change, how much index shift you are getting. That also depends on that. Those are three things.
Roshmi Chatterjee from our department. Can this phenomena be applied to Fabry-Perot resonator with varying refractive index?
Well, yeah. I mean, so yes. I mean, short answer is yes. And there have been some work now. We are also doing some work where we ask ourselves that if you have a window, temporal window where refractive index is different than the outside, just like when I said you send a pump pulse, you can create a window of higher index. So in this window now it has two boundaries which have a different refractive index change. It's like two mirrors if you want. So that's a Fabry-Perot essentially. And now you can come from outside and ask yourself under what conditions you can transmit. Are there modes or resonances of the Fabry-Perot? And all these exist essentially. We are looking into that. So answer is yes. You can create a Fabry-Perot with two temporal boundaries, and you can ask yourself what happens. Are there under what conditions pulse get transmitted? Under what conditions pulse get reflected? You can do that. You can even have multiple boundaries. In fact, if I go beyond that, I guess you can make a time crystal essentially. In other words, you can have a bunch of boundaries. You can have multiple boundaries, which will create like a grading, but in time domain grading, a time grading if you want. Which sometimes people start calling time crystal. If you want. So you can have a time grading, and then you can ask yourself what kind of things can happen in this grading. And we have not looked into that yet, but there are a lot of things can be done here. Yes.
Priyank Shah, how much of the beam can be usually reflected? Can such system compete with nonlinear methods for frequency shift?
I don't think I get the question right, but I think in practice, people use nonlinear effects to make this boundary, this sharp boundaries. People are going to use the nonlinear effect. Most people use nonlinear effects to make time lengths, and similarly nonlinear effects to have this temporal reflection. So in practice, yes, use nonlinear effects.
Another question from Roshmi, can the magnitude of reflected and the transmitted beam be calculated?
Yes. Yes. We recently published a paper just about a month ago, actually. There's a paper where we show how to calculate the reflection and transmitted pulse shapes, and what if there's a pulse shape distortion or not, or things like that. So we have done a paper recently on that. Yes, it can.
Okay. So another question from Shomen Odhikari. If the refracted pulse is moving slower than the speed of the boundary interface, then the speed of the boundary must be comparable to c. So how to move the interface so fast, and how to measure?
Well, it's a relative. If the pulse is moving slower than the interface will come to the pulse. I mean, you can think of it. I mean, it depends when you interface is and where your pulse is. If pulse is, if there's an interface, let's say there's an interface here, and the pulse is here, then you have to move it this way, right? But if interface is here, is moving slower. But you can put a pulse on this side too. I mean, you can have a pulse this side or that side. So either the pulse will approach the interface, or interface will approach the pulse, depending on which one is moving slower or faster. So you have to locate, relative location of the two tells you which way it can go. But the effect is there in both cases.
So boundary in temporal domain, what does it physically mean? And how shall we actually realize?
Yeah, so that's what I talked near the end. I can only think of moving boundaries. Because if you want to make a static boundary, then you have to change the refractive index everywhere in space. And that's very hard to do. At certain time, you change the refractive index everywhere in space to make a time boundary, static time boundary. And that's not easy to do. So what we do, we make a moving time boundary. And this we can create by many ways. You can have a modulator, and you apply a sharp voltage, to the modulator. And this basically a microwave pulse, if you want. A microwave pulse will move, but at the region where you apply the microwave pulse, refractive index will be higher. So you can create a higher refractive index region by applying a microwave pulse to a modulator, for example. That's one way. The second way, you can send a pump pulse, a strong pump pulse in a nonlinear medium. So wherever the pulse exists, refractive index will be larger because of the Kerr nonlinearity on that. So you can create moving boundaries either using nonlinear effects or using the electro-optic effect, essentially, those two ways. And that's the way we think we can do it. That's easy to do. So you create some sort of high refractive index window in some region, and then you reflect from it, or whatever you want to do, you adjust the situation that a probe pulse comes in and get reflected or get trapped or whatever. So that's how we do it, two ways.
So Joy Bhattacharya, she has asked that simulation have been done using which software?
Oh, this is a standard split step method that I use for nonlinear effects. It's the same. It's a similar. I mean, because even though I talk about time boundary, this is like a nonlinear term on this on the right side, essentially. So you can use the same problem that you use to solve nonlinear Schrödinger equation. You can use the same method to solve this problem. Because you have a time-dependent refractive index, and that's what the Kerr nonlinearity does. So the problem software is the same. It doesn't change. It's the same program that I use for solitons and other things. The same thing. It's the same software. It's just the interpretation changes. Our way of thinking changes, but not the software.
And Professor Prashant Datta from IIT, why velocity of the boundary is not a parameter on the effect?
It is not a parameter because I am working in a moving frame, and my moving frame is moving at the boundary of the velocity of the boundary. So it is a parameter, but it's hidden. It's not into the equation directly. So I'm assuming my boundary is static in this moving frame, but it is contained in this parameter delta beta 1, which is the relative speed of the pulse with respect to boundary. So that parameter actually has the information about the speed of the boundary. It is contained there in that parameter. But a good question. Yeah.
Another question from Roshmi. Sir, can time transformation approach be applied when we consider the nonlinear parameter to be complex?
Oh, I see. Well, that's a good question. I don't think I have looked into that. I can't answer right away without looking into it, because I always assume in the time transfer problem, I always assume N2 is real. So I don't know the answer. I mean, I've not thought about it. But it's a very good question. Yes.
Professor Prashanta Datta, how to decide on the parameter of dispersive element for application of DFT?
Oh, for DFT application actually is actually all you need is a, so in other words, you take any let's say you take a fiber and you know its dispersion parameter. So anytime you buy it, they give you dispersion parameter. So you can, then you have to find out how much length you have to use. So the condition is the beta 2 times L, the net dispersion of the fiber, is much larger than the pulse width square, essentially. So if you have a pulse width is given to you, you can square the pulse width, and then you multiply beta 2 by the length of the fiber. And make sure this beta 2 L is much larger than pulse width square. That's all.
Okay. So thank you, sir. So many questions.
Oh, that's good. I'm glad to hear that. I'm glad.
Hey, Mosumi, I will ask some questions.
Okay,
Yeah.
sir. You ask.
Professor Agarwal, sir. Hello?
Yeah, sure.
My question is that I have seen some paper in physical review letters, I think around few years ago, that if you compensate spatial diffraction and the nonlinearity in the y and z direction and in the y and x direction and transverse direction, and in longitudinally spatial temporal domain linearity, optical nonlinearity, then there is a light bullet. Can you combine these two?
Oh, that might be hard. Yeah, I see what you mean. I see. No, that might be harder to combine the two. I don't know, because it's already very hard to do what we do here. And if you, so basically you're saying, you're saying if I have a spatial temporal solidon, it's like a bullet, like a thing.
Light bullet.
Light bullet. If I have light bullet, I guess you can, but this will be a very hard thing to do, because then it will include diffraction effects or transverse effects into the problem.
Temporal domain.
Yeah. So you have to include time, but also you have to include diffraction and dispersion both. Because then you can have a spatial temporal soliton or optical or light bullet, essentially. I mean, light bullet requires balance between diffraction and dispersion, right? It requires both of them to make a light bullet. And so if you want to see whether light bullet can propagate through, I guess in some way you can do it, but it will be hard to simulate or do simulations, because you have to solve a 4-dimensional problem with both the x, y, z, and time. And that may be much more difficult computationally. So I think you can do in the lab, certainly. That's not a problem. But to do simulation for this problem will be very time consuming, I think.
My second question is just very simple curiosity from undergraduate teaching point of view, that you have taken, say, pulse wide comparable to the waveguide wide picosecond. So in diffraction, we have seen that single slit diffraction dimension of the obstacle is of the order of the light wavelength. How, if a student asks me how I can physically help him to visualize, and what will be the physical terms of that waveguide dispersion, that means this is the my dimension of the obstacle, and this is my dimension of the wavelength of light. So what will be your counterparts in this concepts? That I like to know.
So essentially, I was comparing what I was doing to a spatial waveguide, which is the standard waveguide where you have a high index layer surrounded by 2 lower index layers. I mean, if you have a normal waveguide, in that case, if you want to confine the light beam into the waveguide, you have to match the width of the beam with the width of the waveguide. I mean, you have to do mode matching, what we call mode matching. So I was not thinking of a simple, I was not thinking of a simple dimension like compared to wavelength. Typically, the waveguide could be multiple wavelength. I mean, and you can have modes. And then what I'm saying is that the width of the input beam, if it is too large or too small compared to the width of the waveguide, then you will not mesh the modes. And in that case, lot of power will be lost. But if you can mesh the modes, if you mesh the width of the beam with the width of the mode, then you can waveguide, you can confine the light into this waveguide. So just like in the spatial case, we need a mode matching. I was arguing that in temporal case also, we need a mode matching. We need to match the input pulse width with the size of the my temporal window, essentially, in that case.
Okay, thank you.
Yeah.
Maushami, so could I conclude, Maushami?
Yes, you can conclude. You conclude. After that, I will.
I have one question. Can I ask? Just
Yes.
just simple question. That
yes,
so,
yes, Vinod.
Yeah, when you send a plane wave through a moving grating, say ultrasonic wave is propagating through a medium, say fused silica, and if you send a plane wave light through it, then the diffracted lights also get different frequencies. Frequency shifts are there in the yeah. So this is a CW light, but still you are getting the frequency. So this is simple phenomena we know that you can imprint the frequency. Yeah, imprint the grating frequency to the diffracted lights. Diffracted lights.
I see.
Yeah.
I didn't know about this effect, but it sounds very interesting and maybe related actually. So I will. You can send me some reference for this, and I will take a look.
Yeah. Okay, sir. Thank you, sir. Thank you very much.
Okay.
Okay.
So when there is no question, so let me once again thank Professor Gobind P. Agarwal for his very, very illuminating and scintillating lecture and to enrich us with his ideas in this emerging field. And may God bless him. And still he is working, and it is a source of inspiration to us. And also I thank Professor Maushami Basu and the other organizing leaders of this workshop to organize this thing and give me an opportunity to chair the most prestigious session of this workshop. So let me thank you all, and I now refer to Professor Maushami Basu.
All right, so I will say bye to everyone.
I'm extremely thankful. Sir, please don't leave for just
Please
1
wait, sir.
minute.
Yeah.
We'll take a screenshot.
So I'm
Okay,
extremely
all right,
thankful.
okay.
I'm extremely thankful to you, Professor Agarwal, for
Okay, all right.
for accepting the invitation and delivering such a lucid presentation. And we have gained so much academically in this presentation. And this novel approach on space-time duality in optics has tremendous potential applications we have understood. And I personally feel that the people along with myself working in the area of optics have been enriched a lot by this talk. So we hope in future also we will be in touch with you regarding the research works in this domain. Okay,
So,
sir, I am very much.
Yeah,
So
no, I will be happy to. I will be happy to. If you want to send me email or something, you have a question, you can send me email. That's fine.
Okay.
I may not always answer, but I will try to answer.
Okay, sir. Okay, sir. The students want to interact with you.
Okay, all right. Okay.
Okay. So I'm also thankful to Professor Somnath Sarkar for chairing the session. And our students wish that a photograph will be taken so that they will take a screenshot. So if all of us put our video on, the screenshot can be taken. And after that, we'll end up this session. Okay. So please put on your video. All of you, please put on your video. Then they will take a screenshot. And after that, we'll just leave. Is it done?
Okay. Good night to everyone.
Okay. Thank you, sir. Good night. Good night.
Okay.
And
We'll meet tomorrow at 10 o'clock.
Okay.
Okay.
Okay, thank you.
Thank you. Thank you, everyone, for attending this session.